Well, hello there, my friend. I'm glad you found your way back here tonight. Wherever you are right now, curled up under a blanket lying in the dark with your eyes already half closed, thank you for choosing to spend this quiet hour with me. Get comfortable. Tonight we're going somewhere very old and very strange. In the middle of the Cold War, buried under the ice of Greenland inside a tunnel city lit by electric bulbs and warmed by a small nuclear reactor, a scientist half a world away sat alone with a thin sliver of ancient ice under his instrument. And when the numbers came back, his hands went still. Somewhere inside that frozen piece of a lost world, the planet's temperature had jumped by nearly 10 degrees Celsius, almost 18 degrees Fahrenheit in less time than it takes a child to grow into an adult. And it had happened before, again and again, 25 times. Before we slip into tonight's story, if slow, honest storytelling like this is something that helps your mind switch off, at the end of a long day, hitting that subscribe button costs you nothing, and it means more to this little corner of the internet than you might guess. And if tonight's story stays with you after the video ends, leaving a like or a few words in the comments helps another tired soul out there find their way to this same quiet room. I would love to know, where are you tuning in from tonight and what time is it right where you are? Go ahead and tell me down below. I look through every single comment, even the short ones. Now, dim the lights if you can. Maybe let a soft fan hum somewhere behind you, and let's begin. Copenhagen, the winter of 1968. Outside, the city was doing what Danish cities do in December. Snow fell without much enthusiasm. Street lamps blurred into soft orange halos above empty sidewalks. Somewhere out there, people were walking home with their collars up, thinking about dinner, thinking about nothing in particular. But inside a quiet laboratory at the university, one man was not thinking about dinner at all. The room around him was small and a little cluttered, the way most rooms get when someone spends more hours in them than in their own home. A single lamp burned over his desk. A mass spectrometer, an odd boxy machine of dials and glass tubing, ticked and hummed against the far wall like something breathing. Beside his elbow sat a cup of coffee that had gone cold hours ago, forgotten the moment it was poured. None of that mattered to him right now. His eyes were fixed on a narrow strip of paper slowly feeding out of the machine, one careful measurement at a time. His name was Dansgaard, and by that point in his life he'd spent almost 2 decades falling in love with something most people would find unbearably boring. Snow. Not snow the way you or I think of it. Not snowmen, not snowball fights, not the kind of snow day that gets children excused from school. Dansgaard loves snow the way a detective loves a fingerprint, because buried inside every single snowflake that has ever fallen on this planet is a tiny invisible signature. A fingerprint made of oxygen. Let me explain gently, because this part matters more than it sounds like it should. Water is made of hydrogen and oxygen, simple enough. But not every oxygen atom weighs exactly the same. Some are very slightly heavier than others, and scientists call these different weights isotopes. Here is the quiet magic of it. When the weather is warm, water molecules built from the heavier kind of oxygen evaporate into clouds a little more easily. When the weather turns cold, those heavier molecules tend to fall out of the sky first, as rain or snow, leaving the clouds a little lighter behind them. Which means if you could measure the ratio of heavy oxygen to light oxygen inside a single snowflake, you could tell, almost like checking a thermometer, how cold or warm the world had been on the very day that Snowflake was born. Dansgaard had stumbled onto this idea back in 1952, almost by accident, while working with a second-hand mass spectrometer in a laboratory that did not have much else for him to do. He was a young man then, the son of a family that ran a small engraving shop in Copenhagen. Not exactly the background you would expect from someone about to change the way humanity understood its own planet. But here is the thing about Dansgaard that his friends and colleagues loved to mention, half joking, half in awe. Once an idea took hold of him. He simply did not let it go. 2 days after being offered a research post built entirely around this strange new method, he said yes. 3 weeks after that, he got married, and 4 months later he and his new wife were aboard a ship sailing toward Greenland, toward the coldest, whitest, most silent place most newlyweds have ever chosen for a honeymoon. If that is not devotion to your job, I honestly do not know what is. For years afterward, Dansgaard collected snow and rain and ice from wherever he could find it. Icebergs breaking off the coast, glaciers, weather stations scattered across the globe. He was in the nicest possible sense obsessed. But snow only falls so deep. If he truly wanted to look far back in time, decades, centuries, tens of thousands of years, he needed something far older than snow. He needed ice that had been sitting undisturbed layer, stacking quietly on layer for longer than human civilization itself had existed. And in the far north of Greenland, something extraordinary had already been built. Something that at first had nothing to do with science at all. In the late 1950s, the United States Army carved an entire small city directly into the Greenland ice sheet. They called it Camp Century. Picture this for a moment because it is truly worth picturing. Tunnels cut through solid ice wide enough to drive trucks through, strung with electric bulbs, warmed in part by a small nuclear reactor, humming away beneath hundreds of feet of frozen white silence. Soldiers slept down there. The base had its own chapel, its own barber shop. Above ground, frozen gusts scraped across a landscape with nothing on it for hundreds of miles. Below ground, in the quiet corridors, the air smelled faintly of diesel and machine oil, and the low mechanical growl of the reactor never fully stopped day or night. Officially, the whole place was described as an Arctic research station. Underneath that description sat far more secretive Cold War ambitions that would not become public knowledge for many years afterward. None of that mattered much to Dansgaard. What mattered to him was one particular achievement quietly buried inside all that military engineering. While building Camp Century, engineers had drilled a narrow tube of ice straight down through the ice sheet all the way to the bedrock below. A single continuous column over 1,300 meters long, close to 4,500 feet, pulled up out of the earth in careful segments like an impossibly long, impossibly cold layer cake sliced the wrong way around. Every layer in that tube of ice marked a year, sometimes more than 1 year pressed close together by the weight of everything above it. And the deepest layers had been resting there undisturbed since long before the last ice age had even finished. Dansgaard heard about this core the way most great discoveries in history seem to happen, sideways, through a passing conversation, almost by luck. He travelled to Camp Century himself in 1964, hoping to see the drilling with his own eyes. But this was a military site in the middle of a tense decade, and the people running it were not in the business of giving tours to curious Danish scientists. He was allowed onto the base. He was not allowed anywhere near the actual drill. So he waited. For 2 more years he waited, sending letters making the right kind of persistent, polite noise that eventually gets things done in science, until an American researcher named Chester Langway, who'd been overseeing the ice coring project, finally agreed to let Dansgaard's small laboratory in Copenhagen analyze samples cut from the core. And that at last brings us back to that snowy night in 1968, in a quiet room at the university, where Dansgaard sat with slice after slice of that ancient ice, melting each one down with great care, running the water through his instrument, and plotting the ratio of heavy oxygen to light oxygen against the depth it had come from. Depth in this case meant time. The deeper the ice, the further back he was looking. For months the numbers behaved exactly the way he expected. A slow, gentle drift downward as he moved into colder, older layers, then a slow drift back upward again, matching what scientists already believed about the shape of the Ice Age. A long, cold, mostly uneventful stretch. Tens of thousands of years of more or less the same freezing weather until the planet finally gradually warmed its way out of it. Slow, gradual, almost sleepy if you will forgive the word given what kind of story this is. And then somewhere down in the older layers the line on his graph did something it was never supposed to do. It jumped, not drifted, not slid. It jumped sharply and dramatically as though someone had reached into the deep past and flicked on a switch. According to what the ice was telling him, within the span of only a few decades less time than a person needs to raise a family and watch their children grow up and start families of their own, the temperature over Greenland had risen by something close to 10 degrees Celsius, 18 degrees Fahrenheit. A shift that in our modern conversations about climate entire decades are now spent arguing over a single degree at a time. Dansgaard, by every account from the people who knew him, was not an easily rattled man, but this stopped him cold. He set his pen down. He stood up, walked the few short steps to the window and stood there for a moment watching the snow fall past the glass orange under the street lamp, endless and unhurried. Then he walked back to his desk and looked at the strip of paper again as if it might have changed its mind while his back was turned. It had not. His first thought, the same thought any careful scientist has when the data looks too dramatic to be real, was that something must have gone wrong. A contaminated sample, a miscalibrated instrument, a small human mistake somewhere between the ice and the machine. So he checked, and checked again. He ran the numbers a second time, then a third half, hoping the strange jump would smooth itself into something more sensible, something more in line with everything he and every other scientist alive at that moment in history had been taught to believe about how climate behaves. It did not smooth out, and worse, or perhaps better, depending on how you choose to look at it, it was not alone. As he kept working his way down through the older sections of the core, he found the same shape again, and again. A sudden violent jump upward, followed by a slow gradual slide back into cold, repeating itself over and over, buried at different depths at different moments in the deep and distant past. There is a particular kind of silence that settles over a laboratory late at night, when a scientist begins to suspect they might be looking at something nobody else has ever seen. It is not the ordinary quiet of an empty room. It sits heavier than that. Dansgaard sat there in the glow of his instrument, while snow kept falling outside on a city that had no idea what had just happened, a few floors above its quiet streets, and slowly understood that the story everyone believed about the Ice Age, calm, slow, unchanging, might simply be wrong. The planet, it seemed, had a heartbeat, and somewhere in its deep frozen past that heartbeat had not always beaten gently. It would take Dansgaard until 1969 to publish these findings properly inside the pages of the journal Science under a title far more modest than the discovery deserved. It would take another 2 decades, several more ice cores drilled from opposite ends of the Earth, an entire new generation of scientists, and more than one heated argument at international conferences before the wider world of climate science fully accepted what one snowy Copenhagen night had already revealed. But it started here. With one careful man, one tube of impossibly old ice pulled up from beneath a secret military base, and one stubborn, impossible jump on a graph that simply refused to behave, because sitting quietly in that room with him now was a question we're going to spend the rest of tonight trying to answer together. If the Ice Age was never the slow, sleepy, unchanging world every textbook on Earth described, then what exactly had it truly been instead? And why, for so many decades before this one frozen night, had almost nobody thought to ask? That is exactly where we need to go next. To answer that fairly, we need to step back much further than a Copenhagen winter and one puzzled man staring at a strip of paper. We need to go all the way back to the world that ice had actually come from, because most of us, if we are honest, are carrying around a picture of the Ice Age that is almost entirely wrong. Close your eyes for a second if you are the kind of person who can listen and picture things at the same time. What comes to mind when I say the words Ice Age? Probably something still. Something frozen in place like a photograph. Endless white plains. A cold that never lifts century after century, millennium after millennium, one long unbroken winter stretching from one horizon to the other. Slow, silent, almost peaceful in a bleak sort of way. That picture is not entirely fiction. Parts of it are true, but it is missing something enormous, something that took science the better part of 100 years to notice, and it is worth sitting with for a moment, because the missing piece is really the whole point of tonight. Let's start with what people actually got right. Around 115,000 years ago, the planet began sliding into what climate scientists now call the last glacial period, and by the time it was in full swing, the world looked almost unrecognizable. Ice sheets more than 2 miles thick sat where Chicago and Berlin and Toronto now stand, pressing down on the land with so much weight that the crust of the Earth itself bent under it. So much of the ocean's water was locked up as ice that sea level sat roughly 400 feet lower than they do today, low enough that you could have walked on dry land from Siberia into Alaska. Woolly mammoths grazed across grasslands that are now the floor of the English Channel. Woolly rhinoceroses built low and heavy with thick, shaggy coats, pushed through frozen scrub alongside giant deer whose antlers alone could stretch wider than a small car. Cave lions, larger than any lion alive today, hunted on plains that are now underwater off the coast of France, and packs of cave hyenas trailed behind the herds waiting for weakness, and scattered across all of it in small resourceful bands were Neanderthals, and eventually our own ancestors learning to survive winters that could kill an unprepared person in an afternoon. That much science had understood reasonably well for a long time. What it had wrong, or rather what it never had the chance to notice, was the rhythm underneath all of it. For most of the 20th century, if you asked a climate scientist why ice ages come and go at all, the answer you would get involved a Serbian mathematician named Milutin Milankovic, and his story honestly deserves more attention than most textbooks ever give it. In the summer of 1914, Milankovic was newly married, honeymooning with his wife in his home village, when the assassination of an Austro-Hungarian archduke in Sarajevo set off the First World War within a matter of weeks. Because he was a Serbian citizen living inside Austro-Hungarian territory, he was arrested almost immediately and taken away as a prisoner of war. By his own account, he had the presence of mind, even on the first night of his imprisonment, to keep working through his calculations by hand, using whatever paper he happened to be carrying with him. Eventually, through the efforts of a former mentor, he was paroled to Budapest, where the authorities allowed him to spend his days quietly in the reading room of the Hungarian Academy of Sciences, so long as he reported to the local police station once a week to prove he had not run off. He would go on to spend 4 years there, a war unfolding around him, working almost entirely alone on a question that must have seemed to everyone but him wildly impractical for the middle of a global catastrophe. What exactly does the shape of Earth's orbit have to do with the rise and fall of ice ages? By hand, without a single piece of modern computing equipment, Milankovic worked out that Earth's orbit is not a perfect circle, and it does not stay perfectly still. The shape of the orbit stretches and relaxes over a cycle lasting roughly 100,000 years. The tilt of the planet wobbles gently over about 41,000 years, and the Earth itself spins slightly off-center, like a top that has been set spinning and left to slowly drift, completing one wobble roughly every 26,000 years. Layer those 3 slow patient rhythms on top of each other, and you get long-term shifts in how much sunlight lands on the northern hemisphere during summer. Less summer sunlight in the north and snow that falls in winter has a better chance of surviving into the next year instead of melting. Do that often enough for long enough and you build an ice sheet one snowfall at a time. It is honestly a beautiful piece of science. Quiet, patient, mathematical. And through the 1950s, an Italian-American scientist named Cesare Emiliani gave Milankovitch's idea powerful support by studying something almost nobody outside a laboratory had heard of: the shells of microscopic sea creatures called foraminifera, buried in layer after layer of mud on the ocean floor. By measuring oxygen isotopes locked inside those tiny fossil shells, not so different in principle from what Dansgaard would later do with snow, Emiliani was able to sketch out a rough temperature history stretching back hundreds of thousands of years, and what he found lined up beautifully with Milankovitch's slow orbital clock. Long, gradual swings between cold and warm stretched out over tens of thousands of years, so by the time Willy Dansgaard sat down with his own instrument, the entire field of climate science had a working theory, and it made sense, and it was elegant, and it had real evidence behind it. Ice ages came and ice ages went on the slow, patient timescale of planetary orbits. Nothing in this picture allowed for a 10-degree jump inside a single human lifetime. Nothing in Milankovitch's mathematics, nothing in Emiliani's ocean mud had any room in it for sudden violent change. Here is the part I find almost more interesting than the discovery itself, and I want to walk through it carefully because it says something bigger than just this one story. It was not that earlier scientists were careless or unimaginative or missed something obvious sitting right in front of them. It was that their tools were in a very literal sense blind to speed. Think about it this way. Imagine trying to understand a person's entire emotional life by checking in on them once a year. You would see the big picture. You would notice if they'd grown happier over the decade or more tired or more anxious as the years went by. But you would completely miss the Tuesday afternoon they got the phone call that changed everything. You would miss the 3 terrible weeks in the middle of an otherwise ordinary spring. Once a year simply is not often enough to catch a sudden change, even a huge one, if it happens and resolves itself between your visits. That essentially was the situation climate scientists were working with. Mud settles onto the ocean floor extremely slowly, sometimes only a few centimeters every 1,000 years, which means a single sample scooped out of a marine sediment core, a sample maybe the width of your finger, might represent 500 years of history, all blended together, averaged, smoothed. If the temperature spiked wildly for 30 years somewhere inside that 500-year stretch, and then settled back down, the sediment would not preserve that spike as a spike. It would simply blur it into the surrounding average, the way a long camera exposure blurs a moving car into a smear of light instead of a sharp, frozen shape. Nobody was wrong exactly. They were looking through a lens that was not built to catch fast movement. And for decades an entire scientific consensus formed around a picture that was true in its broad strokes and completely misleading in its details. There is another way to picture this if the camera comparison did not quite land for you. Think about trying to reconstruct a person's entire biography using nothing but a handful of family photographs taken once a decade. You would get the outline of a life, a child, then a teenager, then a middle-aged adult, then someone older. But you would have absolutely no way of knowing about the single afternoon that changed everything. The accident, the phone call, the decision made in a hallway that quietly altered the next 40 years. 10 photographs simply cannot hold that kind of detail, no matter how carefully you study them. Ocean mud for most of the 20th century was that same handful of photographs spread across 100,000 years instead of one lifetime. I think there is something almost humbling in that if you sit with it. How much of what any of us believe to be simply true, simply the way things are, is actually just the shape of our current instruments, our eyes, our habits of attention, the particular resolution, so to speak, that our lives happen to be running at? You have probably felt a version of this yourself, even outside of science. Have you ever looked back at a relationship or a job or a whole stretch of your own life and realized that what felt stable and unremarkable while you were living through it was actually full of small, sharp turns you simply were not paying close enough attention to notice at the time? We're all, in a sense, running our own lives at a certain resolution. Most of the time it is enough. Sometimes it hides the truth from us completely. Now let's bring this back down to ground level, because numbers on a graph can only carry an idea so far. I want you to picture something with me for a moment, and I want to be honest about what we do and do not know when we picture it. We will never know her name. Nobody alive will ever recover it. But somewhere on the cold grasslands of what is now Central Europe, roughly 40,000 years ago, in the thick of this unstable, restless ice age, there almost certainly lived a young woman, part of a small band of perhaps 20 or 30 people, who had grown up learning the rhythm of reindeer migrations and the particular silence that meant a storm was coming. She would have known the smell of a hearth fire fed with dried dung and bone because wood was scarce out on the open steppe. She would have known exactly how to study the colour of the evening sky before deciding whether to move the camp at first light. These were not simple people scraping by on luck. They were by any honest measure extraordinarily skilled at interpreting a difficult world. For her entire childhood, the world she knew might have been mild enough that summers brought good grazing and full bellies, an interstadial period in the language scientists use today, warm enough that some of these stretches came surprisingly close to the kind of temperatures we consider normal now, and then within the span of her own adult life, perhaps even within a single decade, that world could tighten its grip. Grasslands could thin. Reindeer herds could shift their migration routes further south, chasing grazing that no longer existed where it once had. Winters that used to be survivable with the right preparation could turn suddenly brutally lethal, arriving earlier each year and staying longer, eating away at the margins that used to keep her people fed through to spring. She would not have understood why. There were no instruments, no isotopes, no way to measure heavy oxygen against light. All she would have had was what her grandmother told her about how things used to be set against what her own eyes were now showing her, and the very human, very universal task of adapting to a world that no longer matched the stories she'd been raised on. Do you move the whole camp further south, chasing warmth that might not be there anymore either? Do you stay and gamble on the old hunting grounds one more season? These were not abstract questions to her. They were the difference between a hard winter and no winter survived at all. This is, I think, the piece that gets lost when we talk about ice ages purely in terms of degrees and decades. Real people lived through these swings, not in some abstract geological sense, but season by season, decision by decision, wondering whether to move the camp, whether to trust an old hunting ground one more year, whether the strange warmth of this particular spring meant good fortune or the beginning of something they did not yet have a word for. Have you ever wondered what your own grandparents would make of how quickly your world has changed since they were your age? Multiply that feeling by 10, and you are somewhere close to what a person living through one of these ancient swings might have carried with them quietly every single season. And here is the detail that still catches me every time I think about it. The scientists who eventually pieced together this hidden violent rhythm were not wrong to have believed in a slow, orderly ice age for so long. They were simply the first generation with a strong enough magnifying glass to see through the blur. Ice, it turns out, does something mud on the ocean floor cannot. Snow falls once a year, and in the right places, in the right cold, undisturbed corner of the world, it stacks up in neat, distinct individual layers, year after year after year, almost like the rings inside a tree. Instead of 500 years blurred into a single smudge, an ice core can offer you 500 separate individual chapters, each one still holding its own weather. That difference in resolution, mud averaging centuries against ice preserving individual years, is not a small technical detail. It is the entire reason a hidden heartbeat inside our planet's past stayed hidden for as long as it did, and the entire reason one man in Copenhagen was able to notice something an entire generation of brilliant scientists working with the very best tools available to them had no way of seeing. It is worth remembering the next time someone tells you a thing simply cannot be true, because nobody has ever measured it before. Sometimes that only means nobody has built the right instrument yet. So here is where the story gets even stranger, and honestly a little more personal, because once scientists accepted that the Ice Age had this hidden, fast rhythm buried inside it, a much harder question started forming behind it. Not just what was happening, but why? What on Earth, or perhaps more accurately, what within the ocean and the ice and the air working together could possibly cause a hemisphere's worth of temperature to swing that violently, that quickly over and over again 25 separate times, like some vast ancient machine quietly resetting itself in the dark? That question would end up pulling in an entirely different kind of scientist working in an entirely different part of the world, chasing something almost nobody expected to matter at all. Something so small, so seemingly forgettable, that most people would have poured it out without a second thought. A bubble of air trapped inside ice for tens of thousands of years, waiting for someone patient enough and stubborn enough to finally listen to what it had to say. And that is exactly the thread we're going to follow now. That patient, stubborn person had a name, and here is a small detail I've always loved about him. Physics was not even his first love. His name was Hans Oeschger, and if you had met him as a teenager growing up in a small village near Zurich, in a house full of music, you might have guessed he was headed toward a stage rather than a laboratory. He wanted to be a musician. That was the plan, or at least the dream, for a good long while. But somewhere along the way, physics pulled harder, and he ended up studying it instead at the Federal Institute of Technology in Zurich. Years later, one of his own mentors, a nuclear physicist named Friedrich Georg Houtemans, joked that he understood exactly why Oeschger felt at home in the subject. Houtemans himself, he said, did physics rather like an artist, which meant in a roundabout way that Oeschger had never really left music behind at all. He had just found a stranger instrument to play. I like starting there because it sets up something important about the man who is about to become just as central to tonight's story as Dansgaard already has. Oeschger was not chasing fame, and he was not chasing a single flashy discovery. He was the kind of scientist who fell in love with instruments themselves, with the quiet, painstaking craft of building something that could measure what nobody had ever managed to measure before. And as it turned out, the entire second half of our story tonight depends almost completely on exactly that kind of person. Here is the puzzle Oeschger inherited as a young graduate student at the University of Bern in the early 1950s. Scientists had recently discovered that a particular kind of carbon, 14 forms naturally in the atmosphere and gets absorbed into every living thing on the planet. Once something dies, whether it's a tree or a woolly mammoth, or a person, that carbon-14 slowly decays away at a steady, well-known rate. Measure how much is left in an old bone or a fragment of charcoal, and you can work out roughly how long ago that living thing died. It is in many ways one of the most elegant tools science has ever produced. But there was a catch, and the catch was brutal. Carbon-14 is rare to begin with, and the tiny bit of radioactivity it gives off as it decays is almost impossibly faint, especially in a small old sample. Meanwhile, the entire planet is constantly bathed in cosmic rays raining down from space, and ordinary laboratory equipment could not tell the difference between one faint genuine signal from ancient carbon and the general background static of the universe itself. It was essentially trying to hear a single person whispering from across a crowded, noisy room. So Oeschger, still working on his doctorate, did something wonderfully stubborn. Instead of accepting the equipment available to him, he built his own. Working alongside Houteman's, he designed a new kind of detector, a cylinder wrapped inside a ring of additional guard detectors, all listening at once. Whenever a burst of radiation hit every detector simultaneously, the machine understood that as cosmic background noise, arriving from every direction at once, and threw it out. Only the rare, quiet signal that showed up in the right place and nowhere else was allowed to count. He had in effect built a room specifically designed to cancel out the crowd, so a single whisper could finally be heard clearly. None of this happened quickly, and none of it happened cleanly. Early versions of the device had to be buried underground, sometimes tucked away in old wine cellars, or mine shafts anywhere with enough solid rock overhead to block out even more of that stray cosmic interference. Picture a young physicist still in his 20s hauling delicate glass and metal equipment down into a cold Swiss cellar, tuning dials by lamplight, chasing a signal so faint it could be drowned out by a stray particle that had been travelling through space for millions of years before it happened to strike his instrument on its way down. The device became known simply as the Oeschger counter, and by 1958 it was quietly setting a new global standard for how faint a signal science could actually detect. Somewhere in the middle of all this careful, unglamorous laboratory work, Oeschger also found time for an entirely different kind of milestone. In 1955, the same year he finished his doctorate, he married a woman named Dori Häuptli. 2 years later, they had twin daughters. By every account, he was the sort of father who brought his work home with him in spirit, if not in equipment, endlessly curious, endlessly patient, the kind of man who could apparently explain a complicated idea to a child without making it feel complicated at all. While Dansgaard on the other side of Scandinavia was out chasing snowflakes across icebergs and weather stations, Oeschger was building his career quietly, methodically in a laboratory in Switzerland, raising a young family, refining an instrument almost nobody outside his field had ever heard of. It is a nice reminder, honestly, that scientific history does not only belong to the dramatic lightning bolt moments. Sometimes it belongs to people who simply keep showing up year after year, tightening one more bolt on one more instrument, until the instrument is finally good enough to hear something extraordinary. Neither man could have guessed yet how directly their two very different obsessions were about to collide. By the early 1960s, Oeschger had begun turning his extraordinarily sensitive counter toward a new kind of sample, and this is where his story finally starts braiding into the one we already know. In 1962, he used it to measure something called tritium, a radioactive form of hydrogen inside old compacted snow and ice. What he proved, almost as a side note at the time, was enormous. Ice was not simply a frozen photograph of temperature the way Dansgaard had been using it. Ice could hold an entire library of different kinds of information locked inside the same block, waiting for the right kind of question and the right kind of instrument to unlock each one. That same year, at a gathering of glaciologists, Oeschger crossed paths with the two other men who would end up shaping this entire field of science alongside him, Willy Dansgaard and an American researcher named Chester Langway. By all accounts, it was not a dramatic meeting. No lightning bolt of destiny, just three scientists at a conference, recognizing that their separate skills fit together almost perfectly. Dansgaard could measure temperature from oxygen. Langway had access to the drilling and the cores themselves, including the one pulled up from underneath that secret base in Greenland we have already spent time with tonight. and Oeschger could listen for whispers buried inside the ice that neither of the other two had the equipment to hear. Here is the piece of this story that still gives me a small chill every time I think about it, and I suspect it might do the same for you. When snow first falls, it is soft and loose, full of air. Over years, as more snow piles on top, the weight compresses the layers underneath into something scientists call firn, a dense granular halfway stage between fresh snow and solid ice. And as firn keeps compressing further, eventually the air pockets trapped between the grains get sealed off, completely pinched shut, cut off forever from the atmosphere above. What is left behind, frozen inside that ice, is not a symbol of the ancient atmosphere. It is not a measurement or a proxy or an educated guess. It is an actual physical sample of the air itself, the very same molecules that once drifted over a herd of mammoths or settled quietly above a hunting camp on the tundra, sealed shut and left, completely undisturbed for tens of thousands of years. Oeschger understood faster than almost anyone else alive at the time exactly what that meant. If you could carefully melt that ice under the right conditions without letting modern air leak in and contaminate the sample, you could release those ancient bubbles and measure directly, honestly, precisely what the atmosphere itself was actually made of, long before anyone existed who could have written it down. Can you imagine being the person to first hold a breath of air that nobody has taken in 40,000 years? It took years of careful, unglamorous engineering to get the extraction process reliable enough to trust. But by the end of the 1970s, Oeschger's small team in Bern, often simply called the Bern Group by other scientists in the field, had pulled off something remarkable. In 1979, they published results showing that during the depths of the last glacial period, the concentration of carbon dioxide trapped in that ancient air was almost 50% lower than it is in our atmosphere today. Sit with that number for a second, because it deserves more than a passing mention. 50%. Not a small drift, not a statistical rounding error, but a truly massive difference in the basic chemistry of the air itself, tied directly to whether the planet was locked in an ice age or breathing freely through a warm interglacial period like the one we're living in right now. For the first time in the history of science, nobody had to theorize about this connection anymore. It was sitting there physically in a bubble smaller than a grain of rice. I want to pause here and ask you something gently, because I think it says a lot about who Oeschger was as a person, not just as a scientist. As his team kept extracting these ancient air samples, working their way up through more recent centuries, they eventually reached ice that had formed within the last 200 years. And there, instead of the slow natural wandering they expected, they found something else entirely. A sharp, steep, unmistakable climb in carbon dioxide, matching almost perfectly with the timeline of industrial coal and oil burning across Europe and North America. By every account from people who worked alongside him, this discovery troubled Oeschger deeply, not in a dramatic headline-grabbing way. He was not the type. But those closest to him described a man who had spent his entire career listening patiently to whispers from the deep past, only to realize that the loudest, strangest voice in his own data belonged to his own century. In the years that followed, he went on to build some of the earliest working models of how carbon actually moves between the atmosphere, the oceans, and the plants and soil of the living world, trying to understand not just what had happened, but where all of that extra carbon was likely to end up next. There is something quietly moving about that, I think. A man builds an instrument sensitive enough to hear the faintest echo from 40,000 years ago, and the thing that ultimately unsettles him most is the echo of his own lifetime staring back at him from inside the ice. While all of this was unfolding, Oeschger and his colleagues were also chasing a second, entirely different kind of confirmation, and this part of the story rarely gets told at all. Ice cores are remarkable, but they only exist in a handful of very specific, very frozen places on Earth. If the abrupt climate swings Dansgaard had already discovered were real, truly real, and not some strange quirk limited to one particular patch of the Greenland ice sheet, there ought to be evidence of them somewhere else entirely, somewhere with no ice at all. Oeschger's team found exactly that kind of evidence far closer to home than anyone expected in the mud at the bottom of a small, unassuming lake near Bern called Lake Gersensee. It is worth pausing on how ordinary that lake sounds, because that is rather the point. This was not a dramatic polar expedition, no tunnels, no reactors, no month spent camped on an ice sheet. Just a quiet stretch of water that generations of local families had probably fished, swum in and driven past without a second thought. Buried in ancient layers of lake sediment in the chemistry of tiny shelled creatures that had lived and died in that water thousands of years earlier, Oeschger's colleagues found the same abrupt signature Dansgaard had already pulled out of Greenland's ice. The same sudden warming, the same slow slide back into cold. Not identical in every number, but unmistakably part of the same story. Why does that matter so much? Because it meant the strange heartbeat buried in Greenland's ice was not a local ghost story. A lake in Central Europe with nothing whatsoever in common with the Greenland ice sheet, except sharing the same sky, had been keeping its own quiet diary of the very same events. When two completely unrelated witnesses, one frozen, one liquid, one in the Arctic, one in the middle of Switzerland, tell you the same story independently, a scientist starts to trust that story a great deal more. There is one more piece of Oeschger's thinking worth planting here tonight, even though we are not ready to fully unpack it yet. By 1984, turning all of this evidence over in his mind, Oeschger began to suspect that the culprit behind these wild swings might not be sitting in the atmosphere at all, but somewhere far heavier and far slower, deep within the ocean itself. He described it using a simple household image, a flip-flop switch, the kind that snaps cleanly from one position to another rather than sliding smoothly between them. Something in the great, slow circulation of ocean water he suspected was capable of flipping between two entirely different states, almost without warning, dragging the climate of an entire hemisphere along with it. That idea would not be fully proven during his own lifetime. Hans Oeschger died on Christmas Day in 1998, in the same city where he had spent his entire working life, having spent more than 4 decades teaching an entire generation of scientists how to listen for whispers inside solid ice. Today, a research centre in Bern carries his name. So does a windswept cliff on the edge of Antarctica, about as far from that quiet Swiss laboratory as it is possible to stand on this planet, which feels, if you ask me, like exactly the right kind of tribute for a man who spent his life listening to places nobody else thought to check. What strikes me most looking back at both of these men together is how differently they arrived at the same astonishing truth. Dansgaard was chasing temperature obsessed with a single number hidden in the weight of an oxygen atom. Oeschger was chasing composition patient enough to rebuild an entire instrument from scratch just to hear a whisper of ancient air. Two completely different questions, two completely different tools, and yet they kept landing independently on the exact same impossible rhythm hidden in the same block of frozen time. Maybe that is worth remembering the next time you're stuck on a hard problem of your own. Sometimes the answer does not come from thinking harder about the same question everyone else is already asking. Sometimes it comes from someone standing a little to the side asking an entirely different question and stumbling into the very same truth from a completely unexpected direction. And that flip-flop switch Oeschger described sitting quietly in the deep ocean waiting to snap from one state to another is about to become the centre of everything we still need to understand tonight. Because if something that size really can flip that fast, The next question practically asks itself, what exactly would it take to throw that switch? To throw a switch that size, you would need something enormous behind it. And the man who first started to seriously suspect what that something might be came from about as far away from a glacier as you can get, both in miles and in mindset. His name was Wallace Brooker, and if you had told the teenage version of him that he would spend his life carefully dating events from tens of thousands of years in Earth's past, he probably would have laughed you out of the room. He grew up outside Chicago, the son of a man who ran a gas station in a devoutly religious household that took the story of creation literally down to the number of years involved. In that house, the planet was not ancient. It was young, only a handful of thousands of years old, and that was simply understood the same way you understand which way is up. He went off to a small Christian college in Illinois with modest plans, honestly almost funny in hindsight. He was thinking about becoming an actuary, someone who spends a career quietly calculating insurance risk. Not exactly the resume line you would expect from a future giant of climate science. But a classmate of his, a young man who would later go on to study moon rocks for the American space program, talked him into applying for a summer internship at an Earth Science observatory outside New York. That single summer changed the entire shape of his life. Working under a geochemist at the observatory, a Wheaton graduate himself as it happened, young Brooker got his hands on something brand new at the time, a technique for dating old material using radioactive carbon, the same underlying idea Hans Oeschger, half a world away in Switzerland, was independently obsessing over with his own detectors. Brooker fell for the work immediately and completely. Some of his fellow students, half joking, half not, started calling him, and the other religious kids at the lab the theochemists. It could have stung. Instead, by his own later description, that laboratory came to feel like a kind of personal paradise, the one place where his two great loves, careful measurement and enormous questions, were finally allowed to sit in the same room together. He switched his major, finished his degree in geology, instead of the path he'd originally imagined, and never really left that observatory again for the rest of his life. Here is what I find quietly remarkable about that. A young man raised to believe the Earth was barely older than a handful of human generations went on to spend the next 6 decades mapping out in exquisite patient detail processes that unfold across tens of thousands of years. He did not abandon his curiosity when it led him somewhere his childhood had not prepared him for. He followed it anyway. I think that says something worth sitting with, whatever your own beliefs happen to be. Sometimes the most honest thing a person can do with their curiosity is let it guide them somewhere they did not originally plan to go. Do you ever notice how the people who end up reshaping an entire field rarely start out looking like the obvious candidate for the job? By the late 1950s, Brooker had earned his doctorate and joined the faculty at the same observatory where he had interned as a student. He would stay there remarkably for the rest of his working life, becoming known among colleagues for a temper people fondly described as volcanic, and for an ability to explain enormous complicated systems in blunt, simple language that stuck in your memory whether you wanted it to or not. Younger scientists who worked alongside him used to say that walking into his office with a half-formed idea was a little like handing a promising sketch to an art teacher who truly cared whether you succeeded and would tell you without hesitation exactly which parts were weak. You always knew exactly where you stood with him, mostly because he told you loudly, and more often than not he turned out to be right. It was by every account an exhausting sort of mentorship. It was also for the students who could handle it, the kind that shaped entire careers. For years, Brooker's attention was pulled toward the ocean, and specifically toward a question that sounds almost embarrassingly simple once you hear it out loud. Why is Europe so much warmer than other places sitting at the very same latitude, Places like Newfoundland and Labrador sitting at roughly the same distance from the equator as much of Western Europe endure brutal, bitter winters. London does not. Neither does Paris. Something was clearly moving heat around the globe in a very particular, very lopsided way, and Breuker set out to trace exactly what that something was. The answer, once it came together fully in his mind, was breathtaking in scale. Picture warm water leaving the tropics near the equator, driven along by surface currents, and the planet's own rotation drifting north through the Atlantic Ocean, carrying enormous amounts of heat with it, the way a hot water bottle carries warmth into a cold bed. As that warm water travels north past the coasts of the southern United States out across the open Atlantic, up along the edges of Britain and Norway, it constantly gives some of its heat away to the air above it, which is precisely why a place like the coast of Norway stays milder than its latitude has any right to expect. But giving away heat comes at a cost. As the water cools, it grows denser, and because it started its journey unusually salty, thanks to evaporation back in the warmer latitudes it came from, that cooling water eventually becomes heavy enough to do something dramatic. Somewhere up near Greenland and the icy seas of the far north, in places with names like the Labrador Sea and the Nordic Seas, it simply sinks, plunging thousands of meters down into the deep, dark Atlantic, disappearing from the surface entirely as though a trapdoor had opened beneath it. Once it sinks, that heavy water does not just sit there. It creeps slowly south along the ocean floor, a cold, dense river moving through the deep dark for centuries, eventually spreading out and mixing into other ocean basins around the world, the Pacific, the Indian Ocean, before it finally gradually warms again, rises back toward the surface somewhere far away, and begins the entire enormous loop over once more. A single lap of this circuit from warm surface water near the equator to cold, deep water somewhere on the far side of the planet and back again can take longer than 1,000 years to complete. Breuker gave this system a name that stuck instantly and completely, the kind of name that turns a complicated scientific idea into something a person can actually picture. He called it the ocean's conveyor belt. And once you have that image in your head, a slow, silent, planet-sized loop of water, hauling heat from the tropics up into the North Atlantic, before diving into the deep and circling the globe, it becomes almost impossible to unsee. The idea did not arrive to universal applause, and it is worth being honest about that, because I think the resistance says almost as much as the discovery itself. For most of the 20th century, oceanographers had quietly assumed the deep ocean was essentially the most boring and dependable part of the entire planet. Slow, enormous, practically eternal. Surface weather might change by the hour, but the deep, cold currents circling the globe were treated almost like geological features closer to mountain ranges than to anything capable of shifting quickly. Breuker was in effect arguing that one of the steadiest, most trusted characters in the entire climate story had a hidden temper, and that it had already lost that temper more than once in the planet's past. Plenty of his colleagues needed real convincing. What finally helped the idea travel far beyond a small circle of oceanographers was of all things a magazine illustration. In the autumn of 1987, an article exploring an ancient sudden cold snap near the end of the last ice age ran in a popular science magazine, accompanied by a hand-drawn diagram of Breuker's looping ribbon-like conveyor, winding its way across a simplified map of the world's oceans. It was clear, it was strangely beautiful, and it did something a dense scientific paper almost never manages to do on its own. It let an ordinary reader with no background in oceanography whatsoever look at a single picture and immediately understand the shape of an idea that had taken decades of painstaking measurement to build. Here is why that image matters so much to everything we have already talked about tonight. If this entire enormous system depends on North Atlantic water being salty enough and cold enough to sink, then the whole loop has a genuine weak point. Fresh water is lighter than salt water. Flood the surface of the North Atlantic with enough fresh water fast enough, whether from a sudden burst of iceberg melt or the runoff of a retreating ice sheet, and you dilute the salty water sitting up there just enough that it can no longer grow dense enough to sink. The pump in a very real sense can stall, and when a pump that size stalls, the consequences do not creep in slowly. Brücke came to believe, and later evidence would strongly support him, that shutting down or dramatically slowing the circulation could switch off the flow of heat into the North Atlantic almost as fast as flipping off a light switch, plunging Greenland and the surrounding region into bitter cold within a matter of years or decades, even while other parts of the planet barely noticed the change at all. He was in his own way arriving from a completely different direction at the very same suspicion Hans Oeschger had already been circling in Switzerland. A vast ancient machine hidden beneath the waves, capable of flipping states almost overnight. Can you imagine spending years chasing a mystery only to realize the invisible hand behind it was not hiding in the sky, or the ice, or the sun, but sitting quietly at the bottom of an ocean the entire time? Stop and notice for a moment what had actually just happened across these three very different corners of science. Dansgaard had proven using nothing but frozen snowflakes that the temperature over Greenland had jumped violently again and again throughout the last ice age. Oeschger had proven using bubbles of ancient air that the atmosphere itself had changed composition in ways tightly bound to those same jumps, and had already begun suspecting some kind of ocean switch behind it all. And now Brücke, arriving from an entirely separate discipline tracing warm water instead of ice or air, had independently built a physical mechanism, a genuine workable explanation for exactly how a switch that size could exist at all, and exactly what might be capable of throwing it. 3 scientists, 3 completely different archives, 3 different countries closing in on the very same hidden machine from 3 different directions, mostly without knowing how close the others already were. That to me is the real marvel buried inside tonight's story more than any single fact or figure. Not one lone genius solving an ancient riddle in a flash of insight, but a slow, patient convergence, decades long, built from ice cores and air bubbles and salt water, each piece gathered by people who had no way of knowing at the time that they were assembling different sections of the exact same machine. It is worth pausing here because I think it is easy to let a sentence like that slide by without feeling its actual weight. We are not talking about a small regional current. We are talking about a truly planetary system water, moving between ocean basins on a journey that can take longer than 1,000 years to complete a single loop, carrying more heat northward by some estimates than all of humanity's power plants combined could ever hope to generate. To put that a little more plainly, imagine every power station on the planet, every coal furnace, every nuclear reactor, every dam running at full capacity, simultaneously and still not quite matching the sheer silent heat output of this one ocean current. Brücke liked to say that without this circulation running the way it currently does, average winters in places like Britain and Northern Europe would likely be colder by something close to 20 degrees Fahrenheit, more than 10 degrees Celsius, a difference that would utterly transform what kind of life those regions could support. He came to think of the whole system as the single most fragile pressure point in the planet's entire climate machinery, the one place where a relatively small nudge could tip an enormous otherwise stable structure into an entirely different state. There is something almost unsettling about how ordinary the trigger sounds once you say it plainly. Not a meteor, not a volcano powerful enough to blacken the sky. Just water that is a little too fresh, arriving in the wrong place at the wrong moment in large enough quantity. It is the kind of vulnerability that rarely makes it into disaster films, precisely because it is not loud enough, not violent enough looking to feel cinematic. And yet, if Broca was right, and by now the weight of evidence overwhelmingly suggests he was this quiet, almost boring mechanism was fully capable of plunging an entire hemisphere into Ice Age conditions within the span of a single human decade. I find myself thinking, whenever I walk through this part of the story, about how often the most dangerous vulnerabilities in any system, whether we're talking about oceans or bodies or relationships or entire civilizations, are not the dramatic ones we spend our energy guarding against. They are the quiet, unglamorous pressure points nobody thought to watch closely, right up until the moment something finally leans on them. Which raises the obvious question, the one I suspect is already forming in your mind if it has not already arrived there fully. Where would a pulse of fresh water that enormous actually come from, out on a frozen, largely empty planet, powerful enough to stall a current carrying more heat than every power station on Earth combined? Broca spent the back half of his long career chasing exactly that question, testifying before lawmakers, arguing with skeptics, writing far more papers and books than most scientists manage in several lifetimes, right up until his death in New York in February of 2019 at 87 years old. Fittingly, by his own request, his ashes were not buried in the ground he had once believed was only a few thousand years old. They were scattered instead into the very ocean, whose secret rhythm had defined his entire life's work, carried out to sea by a colleague on one of the observatory's research expeditions. Becoming in a strange and rather beautiful way, one final small drop added to the very conveyor belt he had spent 60 years trying to understand. A boy who once believed the world began only a few thousand years ago ended his life dissolved into a system that has been quietly circling this planet for far longer than human memory can reach. We're going to need an answer to that question about where all that fresh water came from, and it turns out the ice itself, the very same ice Dansgaard and Oeschger had already been listening to so carefully, was about to hand us one of the strangest, coldest culprits in this entire story. That is exactly where we are headed next. Here is a strange little fact to start with, the kind of thing that sounds almost too small to matter, right up until you realize what it actually means. Rocks do not belong in the middle of an ocean floor hundreds of miles from any coastline buried under layers of the finest sediment on Earth. And yet in the 1980s, a German marine geologist working out of a maritime institute in Hamburg kept finding exactly that. His name was Hartmut Heinrich, and his job, broadly speaking, involved pulling long cylinders of mud up from the bottom of the Northeast Atlantic Ocean, and studying them layer by layer, the same patient, unglamorous work that had already unlocked so much of tonight's story. Picture the process for a moment, because it is worth picturing. A research vessel somewhere out past the coasts of Spain and Portugal, lowering a hollow steel tube down through miles of open water until it strikes the sea floor and punches deep into the mud below, drawing up a perfect, undisturbed column of sediment that has been quietly accumulating one thin layer at a time since long before recorded history began. Back on land, in a laboratory that likely smelled faintly of salt water and drying clay, that tube gets sliced open lengthwise, and a scientist gets to trace straight down through tens of thousands of years in a single afternoon. Ordinary deep-sea mud is about as calm and predictable a material as science ever gets to study. It builds up slowly a few centimeters every 1,000 years, made almost entirely of the microscopic shells of tiny plankton and fine airborne dust settling gently to the ocean floor like snow falling in absolute slow motion. It is fine, it is uniform, it is frankly the least dramatic substance imaginable, which is exactly why what Heinrich found made no sense at first glance. Scattered through his cores at several distinct depths, he kept running into layers packed with something that had no business being there. Not fine ooze, actual rocks. Coarse, gritty, sometimes gravel-sized mineral grains mixed in among the delicate microscopic shells like someone had dumped a handful of driveway gravel into a bowl of flour. 6 separate layers of it spaced out through the sediment record, each one a jarring interruption in an otherwise calm, orderly accumulation of ocean dust. No river on Earth could have carried stones that size that far from land. No storm, no current, no ordinary process anyone could think of came close to explaining it. Let me ask you something before I tell you what it turned out to mean. If you found gravel buried in the middle of the smoothest, calmest floor imaginable, hundreds of miles from any shore, what would be your first guess? Most people understandably guess wrong. Landslide, volcanic ash, some kind of undersea avalanche. The real answer turned out to be quieter and considerably stranger than any of those. There is really only one honest way for a rock that size to travel that far out into open ocean, and then sink straight down through hundreds or thousands of meters of water. It has to hitch a ride. And the only kind of vehicle capable of carrying a boulder out across an open sea and then releasing it precisely directly downward is ice. An iceberg carves off the edge of a continental glacier, and because glaciers spend centuries grinding directly across solid bedrock as they creep toward the sea, they pick up an enormous amount of broken stone along the way, locking it into the ice itself like raisins baked into a loaf of bread. That embedded stone rides along silently for the whole journey, sealed inside a slab of ice that might be taller than a 10-story building and wider than a small town. Carry that iceberg far out into open water, let the sun and the sea slowly do their work, and eventually the ice around each embedded stone simply disappears. The rock, with nothing left to hold it up, drops straight down and settles onto the seafloor exactly where the iceberg happened to be floating at that moment. Geologists actually have a name for this kind of stone sitting alone and out of place in fine sediment or soil that could never have produced it naturally. They call it a dropstone, and once you know to look for it, a dropstone stops being just an odd rock. It becomes a signature, a little stone confession left behind by an iceberg that has long since disappeared, telling you with total certainty exactly where it was floating on the day it finally melted away. Hold one in your hand if you ever get the chance, and you are holding a piece of the actual North American landscape scraped loose by a moving glacier, tens of thousands of years ago, carried hundreds of miles out, across open water inside a floating mountain of ice, and finally set down gently at the bottom of an ocean it had no natural business ever reaching. What Heinrich had actually stumbled onto were 6 separate armadas of icebergs, vast enough and numerous enough to blanket a huge stretch of the North Atlantic seafloor in their dropped cargo. We now call these episodes Heinrich Events, and later research managed to trace the mineral fingerprints in that debris back to a specific point of origin, a region in eastern Canada around Hudson Bay and Hudson Strait, which meant something almost unbelievable had happened there not once, but at least 6 separate times over roughly the last 70,000 years. An entire arm of the enormous Laurentide ice sheet, the ice sheet that once buried most of Canada, and a good portion of the northern United States under ice thicker than most modern skyscrapers at all, had periodically broken apart and poured itself into the sea in catastrophic iceberg-choked floods. Try to picture the Hudson Strait during one of these episodes not as the relatively open navigable channel it is today, but as a churning white groaning corridor of ice choked from shore to shore with bergs the size of city blocks, grinding their way out toward open water for centuries without pause. Here is where the story gets even more interesting, because for a while nobody could agree on why. Heinrich's own original guess back when he first published his findings pointed toward the sky rather than the ice itself some subtle rhythm in Earth's orbit nudging the ice sheet's edge at just the right moments. It was a reasonable first attempt built on the same kind of orbital thinking that had already explained so much about the slow rise and fall of ice ages in general. It also turned out to be only part of a much stranger picture. Other researchers pored back over his data and noticed something the orbital idea could not quite account for. The spacing between these 6 events was not nearly regular enough to match any known celestial rhythm. Something else was clearly setting the pace, something closer to home. That correction did not diminish Heinrich's discovery in the slightest. If anything, it is a rather lovely example of how science tends to work at its best. One careful observer notices something nobody expected to find, offers their best honest guess at an explanation, and then invites an entire community of other careful people to come along and test that guess against the evidence until something sturdier emerges. The rocks were real either way. It just took a little longer to understand what had actually put them there. That fuller understanding would not fully come into focus until a glaciologist at the University of Chicago named Douglas McHale sat down with the physics of ice itself and asked a very different kind of question. What if these collapses had nothing to do with the sky at all? What if the ice sheet was doing this entirely on its own, following a private internal clock that had nothing whatsoever to do with the sun, the seasons, or the orbit of the planet? I want to walk through McHale's idea carefully because I think it might be one of the most quietly astonishing explanations in this whole story, and it rarely gets the attention it deserves. Underneath the Hudson Bay region, the bedrock is not smooth solid stone. It is covered in a thick layer of loose, soft sediment left behind by older, even more ancient glaciations. As long as that sediment stays frozen solid, it behaves like concrete, gripping the ice sheet above it firmly in place, and so century after century snowfalls compresses and adds itself to the top of the ice sheet, which simply grows taller and taller, anchored to that frozen ground going essentially nowhere. But ice, it turns out, is an excellent insulator, and underneath every ice sheet on the planet, heat is constantly rising up from deep inside the Earth itself, seeping outward from the planet's own interior warmth. Normally that heat escapes into the open air with little trouble. Bury it under an ice sheet that keeps getting thicker and thicker though, and it has nowhere left to go. It simply accumulates, trapped, pressing upward against the frozen ground from below for centuries, for millennia, patiently building toward a threshold nobody watching from the surface could ever see coming. Think of it a little like a house with a chimney that has slowly and visibly been sealed shut. The fire in the hearth keeps burning quietly, the same as it always has. Nothing about the fire itself has changed, but with nowhere left for the heat to escape, the room keeps getting warmer and warmer long after anyone inside would have expected it to level off, until eventually something in that sealed room has to give. Eventually that trapped heat does exactly what trapped heat always does. It wins. The frozen sediment beneath the ice thaws from underneath, turning from something as rigid as concrete into something closer to wet, slippery clay, almost overnight in geological terms. And the instant that happens, the enormous, patiently accumulated weight of the ice sheet above suddenly has nothing solid left to grip. It starts to slide. Not gently. An entire river of ice, wider and faster than anything you could picture from an ordinary glacier, comes roaring through Hudson Strait toward the open ocean, disgorging iceberg after iceberg after iceberg into the North Atlantic for centuries on end. Researchers estimate that a single one of these episodes could last anywhere from 2 to 10 centuries, an almost unimaginable span of time for what is, geologically speaking, still considered a single sudden event, until enough of the ice sheet's mass has drained away that the whole system finally cools back down The ground refreezes solid, and the entire slow, silent cycle of building and waiting begins all over again. Scientists gave this elegant, self-contained mechanism a name that I have always found strangely charming for something so consequential. They call it the binge and purge cycle. Sit with that for a moment because I think it deserves more than a passing nod. This means some of the most violent climate disruptions of the entire Ice Age were not at their root caused by anything happening in the atmosphere, or the sun, or even the ocean currents we spent so much time understanding already tonight. They were caused by an ice sheet quietly building pressure against itself for thousands of years, completely independent of whatever the climate happened to be doing at the surface until physics simply forced its hand. It is less like a storm arriving from outside and more like a fever finally breaking after building silently unseen for far too long. We tend to tell ourselves stories about disaster as something that arrives. A storm rolls in, a stranger shows up at the door, something crashes into us from the outside, and life was fine right up until the moment it was not. Heinrich Events quietly complicate that tidy story. Here was a collapse that had been assembling itself patiently and visibly for thousands of years before the first iceberg ever broke free, built entirely out of ordinary snowfall and ordinary geothermal heat, doing nothing dramatic at all until the exact moment it became unstoppable. Have you ever watched something fall apart and assumed at first that it must have been caused by something sudden and external, only to realize much later that the real cause had been quietly building on the inside the entire time for years, waiting for exactly the right moment to surface? That distinction matters enormously for how we understand everything we have covered tonight. It is tempting and honestly quite common to imagine that every one of the 25 abrupt swings hidden in Greenland's ice must share the exact same cause, the same trigger, the same size, as though the whole record were simply one repeating template stamped out again and again. They do not. Heinrich events are rarer and far more extreme than an ordinary swing in the record arriving roughly once every 7 to 10,000 years rather than every 1,500, and when one does occur it tends to coincide with and dramatically deepen whichever cold stretch it happens to land inside. Picture the ordinary rhythm we have already spent hours getting to know as a series of waves rolling steadily onto a shore. A Heinrich event is not simply another wave. It is the moment an entire iceberg fleet arrives and floods enough fresh, cold water into the North Atlantic to seize up Brooker's great conveyor belt directly at its weakest point, turning an already cold stretch into something colder still for centuries longer than it might otherwise have lasted. Out of 25 known swings in the record, only a handful line up with one of these iceberg armadas at all. The rest of the rhythm, the majority of it, was apparently perfectly capable of happening entirely on its own, no icebergs required. So now, if you've been keeping track alongside me, look at everything sitting on the table in front of us. Temperature pulled note by note out of frozen snowflakes. Atmosphere extracted breath by ancient breath from bubbles sealed in ice. A vast ocean engine patiently hauling heat around the entire globe vulnerable at exactly one point. And now an ice sheet capable of quietly building pressure against itself for thousands of years before suddenly catastrophically letting go. 4 completely different mechanisms. 4 completely different scientists working in 4 different countries, publishing decades apart, all circling the very same repeating rhythm from 4 entirely different directions, most of them with no idea how close the others already were. It is a strange kind of comfort honestly realizing how many independent doors led to the very same room. When that many separate lines of evidence gathered by people who are not even looking for each other keep landing on the same underlying pattern, you stop suspecting coincidence and start trusting the shape of the thing itself, which finally brings us to the question we're ready to actually answer properly. Not what caused any single one of these swings, but what the whole pattern looks like laid out end to end, all 25 of them across 100,000 years of frozen time. That is exactly where we're going next. If you have ever tried counting something enormous and very old at the same time, you already know how strange that process starts to feel. Somewhere around the 10th thousand, the numbers stop feeling like numbers at all. They start feeling more like a story you're walking through one careful step at a time, the way a long quiet hallway can start to feel less like distance and more like a kind of company. That is more or less the situation an entire generation of scientists found themselves in, once it became clear that Greenland's ice held not one strange anomaly, but a whole repeating pattern of them. Counting 25 of anything is not usually difficult. Counting 25 wild swings in the temperature of an entire hemisphere buried at different depths inside a 2-mile thick sheet of ice, each one needing its own precise date, its own name, its own place in line, turned out to be a truly enormous undertaking, one that would occupy careful people for decades. Let me show you how they actually pulled it off, because I think the method itself is nearly as remarkable as what it eventually revealed. Picture a freshly cut slice of ice core under bright angled light, the kind of light a technician might position specifically to catch the texture of the surface rather than looking straight through it. Snow that falls in winter tends to carry more dust than snow that falls in summer swept up from dry exposed land elsewhere on the planet during the colder months. Layer enough of these winters and summers on top of each other, and you get something that under exactly the right lighting becomes visible to the naked eye, faint bands of slightly darker and slightly lighter ice stacked one on top of another all the way down. It is not so different in principle from counting the growth rings inside an old tree, except the tree in this case is made of frozen time instead of wood, and a single year might be represented by a layer no thicker than a few sheets of paper stacked together. Near the surface, where the layers are thick and generous, counting them is almost pleasant work. Thousands of meters down, where the sheer pressure of everything above has squeezed decades into a space you could cover with your hand, that same task becomes something closer to deciphering a manuscript that has been slowly, patiently crushed flat. Can you imagine the kind of patience that job actually demands? Sitting for months, sometimes years, counting individual winters one at a time back through tens of thousands of them, knowing that a single miscount early on could throw off everything that follows. Dustbands alone were never going to be enough, though, especially deeper in the ice, where the sheer weight of everything above starts to squeeze each yearly layer thinner and thinner, sometimes past the point where the naked eye can reliably separate one year from the next. So scientists layered on additional methods. One clever technique measures how easily electricity passes through the ice at each tiny interval, since the acidity of each layer, which shifts slightly with the seasons and with events like distant volcanic eruptions, changes how well it conducts a small current. Run a fine electrode slowly down the length of the core, and the instrument effectively hums out a rhythm, faint pulses corresponding to each passing year like a stethoscope pressed against something that stopped breathing tens of thousands of years ago, but somehow never stopped keeping time. And then there is the tool I find almost unreasonably beautiful once you sit with what it actually means. Certain volcanic eruptions, the truly massive ones, throw so much fine ash so high into the atmosphere that it spreads out and settles across enormous portions of the entire planet within the very same year. That ash carries a distinct chemical fingerprint tied to the specific volcano and the specific eruption that produced it, almost like a signature nobody else on Earth could forge. The individual glass shards involved are smaller than a grain of sand, invisible to the naked eye, and yet a careful chemist can pull them out of the ice, measure their exact composition, and match them with startling confidence to one particular mountain on one particular afternoon tens of thousands of years in the past. find a trace of that exact fingerprint inside a layer of Greenland ice, and then find the very same fingerprint inside a cave formation in Austria, or a different one in China, or a marine sediment core pulled from the floor of the Atlantic, and you have just tied 3 or 4 completely unrelated archives scattered across the entire globe to the exact same year in history. Scientists call these matches tie points, and they function almost like nails hammered through separate photographs to pin them all onto the same corkboard in exactly the right order, whether the individual photographs agree with each other or not. Here is a question worth sitting with for a moment. How would it feel to realize that a single volcanic eruption, one violent afternoon thousands of years before anyone had invented writing, left behind a kind of signature precise enough that people today can use it to line up ice from the Arctic with a stalagmite growing quietly in a cave on the other side of the planet? Piece all of this together. The dust bands, the electrical rhythm, the volcanic fingerprints cross, checked patiently against each other across multiple independent ice cores, drilled years and sometimes decades apart, and you get what scientists eventually settled on calling a master chronology, a single carefully agreed upon timeline stretching back roughly 60,000 years accurate, in the more recent stretches to within a handful of years. Once that timeline existed, the whole scattered 25-year-long puzzle we've been assembling together tonight could finally be laid out properly side by side in order each event given a formal name. The system researchers settled on after considerable international discussion was refreshingly plain. The cold stretches became Greenland stadials numbered from most recent to oldest. The warm interruptions became Greenland interstadials numbered the very same way. A gathering of scientists from several different countries, Danish glaciologists who had spent entire careers on the ices, statisticians from Britain, physicists from Switzerland and the United States spent years hammering out exactly where each boundary should fall, occasionally disagreeing rather passionately over whether some smaller, subtler wiggle deserved its own number or simply belonged folded into a neighbouring one. At one point, a modest little interstadial that nobody had originally accounted for turned up wedged between 2 already numbered events, and rather than renumbering everything that came after it, the group simply gave it a decimal, tucking it in as a smaller sibling squeezed between 2 older ones. It is a small, almost comic detail I am fond of that some of the most dramatic climate upheavals in Earth's deep past ended up filed away under names about as poetic as a filing cabinet label. Somewhere between the burning excitement of first discovery and the calm official record we rely on today, an entire discipline had to grow up and start doing paperwork. Laid end-to-end, the pattern is frankly staggering to look at. Roughly 25 separate swings stretching from about 110,000 years ago down to the threshold of our own warm, comparatively calm era, each one following that same unmistakable shape, a sudden dramatic leap upward, completed within a matter of decades, followed by a long, slow, uneven slide back down into cold that could last anywhere from a few centuries to several thousand years before the next leap arrived. Scientists sometimes describe the shape of a single event on a graph as a sawtooth, and once you have seen it drawn out, you cannot really unsee it, a steep, near vertical cliff face on one side, and a long, gently eroding slope on the other, repeated over and over down the entire length of the record like teeth on some enormous ancient blade. Stand back far enough from the whole graph and squint, and the last 100,000 years of Greenland's climate stops looking like a temperature record at all. It starts looking like the jagged skyline of some impossible mountain range drawn by a hand that kept slipping upward before slowly, patiently smoothing itself back down. And here, tucked inside that pattern, sits a mystery that, as far as I am aware, nobody has fully solved to this day. When researchers measured the spacing between these 25 events more carefully, a strange regularity kept surfacing. A German climate scientist named Stefan Rahmstorff was among the first to lay this out clearly. Running careful statistical analysis on the GIS P2 ice core record and reporting a spacing that was not perfectly even, not clockwork precise, but leaning again and again toward gaps of around 1470 years, or a clean multiple of that same number. Which raises an obvious, almost irresistible question. If something is pacing these events with that kind of rough regularity, what on earth, or perhaps more accurately, what beyond Earth could possibly be keeping that particular beat? The Sun was an immediate suspect and then just as quickly seemed to be ruled out. Astronomers know of no solar cycle lasting anywhere near 1470 years. What they do know of are two much shorter, well-documented solar rhythms, one lasting roughly 87 years, the other roughly 210 years, tied to subtle, well-measured changes in the Sun's own activity over time. Neither one on its own comes anywhere close to matching the mystery interval. Then a group of researchers tried something rather clever. What if nature was not looking for a single instrument playing one long slow note, but was instead layering two shorter instruments on top of each other and letting their combined rhythm produce something neither one could manage alone? Feed both of those solar cycles, the short one and the medium one, into a working climate model at the same time, and something remarkable falls out the other end. The two rhythms drift in and out of alignment with each other in a way that produces a new emergent pulse, one that lands with startling consistency right around 1470 years. Not because either underlying cycle actually runs that long, but because of how the two of them happen to beat against each other over time, the way two slightly mismatched metronomes ticking at their own separate speeds will occasionally almost eerily land on the exact same beat before drifting apart again. If you have ever sat in a room with two clocks that were not quite synchronized, you may already have an intuitive feel for this. Most of the time, their ticking simply overlaps in a messy, unremarkable way, easy to ignore entirely. But every so often, for one brief moment, both clocks land on the very same instant together, and something about that small coincidence catches your attention, completely out of proportion to how little it actually means. Braun's model suggested something similar might be happening on a planetary scale. Two separate solar rhythms, each perfectly real and independently documented, occasionally lining up just enough to nudge an already unstable ocean and ice system over the edge, again and again at intervals that average out to something remarkably close to 1470 years. I want to be honest with you about where this stands today rather than wrapping it up more neatly than the evidence actually allows. Plenty of respected scientists remain honestly unconvinced. Some argue the 1470-year spacing is not a true cycle at all, but simply what naturally falls out of a noisy, chaotic system that occasionally crosses a threshold, the way a series of random claps might purely by chance sometimes land close to an even rhythm without any conductor actually keeping time. Other researchers have pointed out that if you only include the handful of most recent, most precisely dated events in your count, the apparent regularity gets noticeably stronger, which is exactly the kind of pattern you would expect to see if the effect were at least partly a trick of limited imperfect data rather than a true underlying signal. Careful statistical reanalysis of the record has gone back and forth on this question more than once, and as far as I can tell, it has not been settled cleanly in either direction. Isn't there something rather moving about that, though? An entire community of serious, rigorous people, decades into studying this rhythm, still willing to say out loud that they are not completely sure whether they are looking at a genuine cosmic heartbeat or a beautiful coincidence dressed up to look like one. In most areas of life, admitting that kind of uncertainty out loud in public in front of your peers takes more courage than simply picking a confident answer and defending it. Science at its best seems to ask for exactly that kind of courage as a baseline requirement rather than an exception. I will admit, of everything we have covered together so far tonight, this is the piece that lingers with me the longest after the lights go out. Not because it hands us a tidy answer, but because it does not. There is something almost human about a rhythm that leans toward regularity without ever fully committing to it the way a skilled musician might play slightly ahead of or behind a metronome on purpose, alive in a way perfect mechanical timing never quite manages to be. Maybe the planet's climate, even at its most violent, was never purely a machine ticking along on rails. Maybe it was always something closer to a living, breathing rhythm, insistent, largely predictable, but never quite willing to be pinned down completely. I find that oddly comforting, if I am honest. We spend so much of our lives wanting the systems around us weather markets our own bodies, our own moods, to behave like tidy machines with dependable settings. Most of them never quite do. Perhaps it is worth remembering that even something as vast and ancient as an ice age could not be pinned down into a perfectly obedient rhythm either, and the planet seemed to manage just fine anyway. We now have the full shape of the pattern, laid out in front of us, all 25 swings, roughly timed, roughly explained, endlessly debated at the edges. But numbers on a timeline, elegant as they are, can only carry a story so far. To really understand what one of these swings actually felt like on the ground to something alive and breathing, we need to stop looking at the whole 100,000-year sweep of it and zoom all the way into just one single event, arguably the most famous, most consequential swing of the entire 25. That is exactly where we are headed next. It began of all things with a flower, not a fossil bone, not a mysterious rock, not an ice core pulled up from underneath a secret military base. Long before anyone had ever drilled into Greenland, a Swedish botanist named Alfred Nathorst was on his knees in a clay pit in southern Sweden in the year 1870, searching patiently through damp grey mud for the pressed, papery remains of a plant most of us have never heard of. Picture the scene honestly, because it was not glamorous work. Cold hands, wet clay under his fingernails, hours spent turning over thin, unpromising slabs of sediment on the small chance that one of them might hold something worth keeping. He was not looking for anything dramatic. He later admitted that on a good day he might find one single identifiable leaf worth keeping. One, and he counted himself fortunate whenever he did. The plant was Dryas octopetala, a small pale 8-petaled wildflower that still grows today in places like Svalbard and the higher, colder reaches of the Scandinavian mountains. It has no interest in warm weather whatsoever. Wherever this particular flower thrives, you can be reasonably certain the climate around it is cold open and unmistakably Arctic. What Nathorst kept finding layer after layer was strange enough to bother him. Buried in these old lake sediments beneath layers containing pollen from birch trees, the unmistakable evidence of a warm forested landscape sat another layer, thick with the leaves of this small Arctic flower. And above that layer the birch pollen returned again as if the forest itself had simply picked up where it left off. Something cold, sharp, and temporary had pushed its way directly through the middle of an otherwise gentle warming trend, and then just as suddenly stepped back out again. A few decades later, two other researchers, Nikolai Hartz and V. Milthers, working through similar clay deposits near Copenhagen, pinned the pattern down properly and gave it the name that has stuck ever since. They called it the Younger Dryas. Here is what I find quietly astonishing about that origin story, and I do not think it gets nearly enough credit. Decades before Dansgaard ever touched a mass spectrometer, decades before anyone suspected an ocean current could behave like a light switch, an entire abrupt climate event had already been discovered correctly, patiently using nothing more advanced than a trained eye, a small shovel, and an uncommon amount of patience for sorting through mud. No funding committee approved this work. No government race to the Arctic backed it. Just one determined naturalist and later a small circle of equally determined colleagues, refusing to dismiss an odd pattern in the mud simply because it did not fit the tidy story everyone already believed. The ice cores would later hand us the precise numbers, but the flower got there first. Have you ever noticed how the biggest discoveries sometimes arrive quietly carried in by someone doing work that looks from the outside almost unbearably tedious? By the time modern dating methods caught up with Nathor's flower, the numbers behind it turned out to be staggering. Around 12,900 years ago, right as the planet was climbing steadily out of the last ice age, warming nicely, forests spreading northward, the whole recovery abruptly reversed itself. Temperatures across much of the northern hemisphere plunged by roughly 5 degrees Celsius within just a few decades, and in Greenland itself the swing was sharper still. The cold snap held on stubbornly for around 1,200 years, an entire Younger Dryas worth of tundra ice and hardship, before ending just as abruptly as it began dumping the planet directly into the warm, comparatively gentle era we still call home today. To put that span in perspective, 1,200 years is longer than the distance separating us tonight from the fall of Rome. An entire civilization's worth of time, spent locked inside a single cold snap that a small flower had already flagged quietly more than a century before anyone thought to ask why. By now tonight you already know enough to recognize the shape of this. It is not a new kind of event. It is simply the most recent, most famous, most thoroughly studied member of the very same family of 25 swings we have already spent hours getting to know. Which meant it also had to have the same kind of trigger hiding somewhere underneath it. This is where Wallace Brooker's ocean engine, the one we spent an entire stretch of tonight tracing across the floor of the Atlantic, finally gets to prove itself on the case it was originally built to solve. In 1989, Brooker and his colleagues proposed a specific testable culprit. Somewhere in the retreating edge of the Laurentide ice sheet, an almost unimaginably large body of meltwater had been pooling for centuries, trapped behind walls of ice like water behind a dam. Geologists call it Lake Agassiz, and at its largest it may have held more fresh water than every one of today's Great Lakes combined, spreading across a footprint of what is now Manitoba, Ontario, and stretches of the northern United States deep enough in places to have swallowed a fair-sized mountain whole. For a lake that enormous to simply vanish is already a strange thing to picture. For it to vanish quickly in a matter of months or a handful of years rather than centuries is closer to picturing an inland sea being poured out through a crack in a dam wall. Brooker's proposal was elegant in its simplicity. At some point near the start of the Younger Dryas, the ice dam holding that lake in check finally gave way, and an outburst of fresh water large enough to reshape entire landscapes came pouring into the ocean, diluting the salty surface water at exactly the spot where it needed to sink and stalling the great ocean engine almost overnight. It was a beautiful hypothesis. There was just one stubborn problem with it, and I think this part of the story deserves real attention because it shows science working exactly the way it is supposed to, slowly, honestly sometimes for decades, refusing to declare victory before the evidence actually arrives. Brooker's original proposal pointed toward one specific escape route, the Great Lakes and the St. Lawrence Valley, out past what is now eastern Canada. It made geographic sense, the most direct line between a lake that size and the ocean current it needed to disrupt. But when researchers went looking for the fingerprints such a flood should have left behind, Along that route, changes in salinity preserved in seafloor sediment, a scoured landscape, sudden shifts in the tiny fossil shells that record ancient ocean chemistry, they came up disappointingly empty-handed. The salt water off the mouth of the St. Lawrence simply refused to show the dramatic freshening a flood of that size should have caused. Something did not add up, and to their credit, the scientists involved did not paper over the gap. They said so plainly in print and kept looking. By 2006, Broca himself admitted in a scientific paper no less, that not being able to pin down the flood's actual path was more than a little unsettling. Imagine spending 17 years confident you had identified the trigger for one of the most consequential climate events in human prehistory, only to be unable to locate the physical scar it should have left on the land. The mystery finally cracked open in 2010, and not where anyone had originally been looking. A research team led by geologist Julian Merton turned their attention thousands of kilometres to the northwest toward the Mackenzie River system, which drains a vast stretch of northwestern Canada out into the Arctic Ocean rather than the Atlantic. There, in gravel deposits and a wide scoured erosion surface that had no business looking the way it did, carved by something far more violent than an ordinary river ever could manage, they finally found what everyone had been searching for. Lake Agassiz, it turned out, had not emptied itself eastward through the St. Lawrence at all. It had drained out through the roof of the continent, sending its floodwaters north into the Arctic Ocean, which then carried that fresh cold water around into the North Atlantic by an entirely different path than anyone had originally guessed. 21 years passed between Broca's original hypothesis and the physical proof of exactly how it happened. I find that gap oddly reassuring, honestly. It would have been easy at almost any point along the way to simply declare the mystery solved and move on. Nobody did. The idea sat there plausible but unproven, patiently waiting for the actual evidence to catch up with it. Can you think of anything in your own life you have believed for years, quietly confident you understood the reason behind it, only to discover much later that the real explanation was hiding somewhere you had never even thought to look? I want to pause here and be fair to the parts of this story that remain honestly unsettled, because a few other explanations are still very much part of the conversation. Some researchers have pointed to a cluster of unusually intense volcanic eruptions right around the same window of time, wondering whether ash and sulfur thrown into the upper atmosphere might have helped tip the climate toward cooling before the flood ever arrived. A smaller, more contested group of researchers has gone further, still proposing that a comet or fragmenting space object struck or exploded above the ice sheet, at precisely this moment igniting continent-spanning wildfires and triggering the whole collapse almost instantly. That particular idea has not found wide acceptance among specialists in the field, and the physical evidence offered in its favour has been challenged repeatedly by other researchers working the same material. I mention it not because I think you should walk away convinced, but because leaving it out entirely would not be honest storytelling. The flood hypothesis remains by a wide margin the explanation most researchers find convincing. But nobody serious pretends every loose thread has been tied off. Now here's where this particular member of the 25 earns its place as the most consequential one of all, and it has nothing to do with ice or oceans at all. On the other side of the planet from Lake Agassiz, in a warm, fertile stretch of land we now call the Levant, a resourceful group of hunter-gatherers, known to archaeologists as the Natufians, had already been living an unusually settled life for well over 1,000 years. That alone was unusual for the time. Most hunter-gatherer groups across the ancient world stayed on the move following game, and seasonal harvests never quite settling down in one place long enough to build anything permanent. The Natufians did settle building small stone-founded villages burying their dead with care and ornament-carving handles for their tools with an attention to beauty that had nothing to do with survival. The Levant at that time was not the dry, dusty landscape many of us picture today. It was closer to open parkland rich with wild wheat barley and other edible grasses growing abundantly enough that a community could gather sizable harvests without planting a single seed on purpose. Archaeologists have even found the charred remains of something close to flatbread made from wild grain dating back roughly 14,500 years long before farming as we normally think of it existed anywhere on Earth. Then the drought arrived. As the Younger Dryas tightened its grip across the northern hemisphere, the wild cereal stands the Natufians had relied on for generations began thinning out, pushed back and outcompeted by hardier, less useful scrub as rainfall dropped and conditions turned harsher. A great many archaeologists believe, though, I want to be honest, that this remains a hotly debated interpretation, rather than settled fact that this squeeze is precisely what nudged some of these communities toward a radical new strategy. Rather than simply following the wild grain wherever it still grew, some groups appear to have started deliberately clearing ground, saving seed and planting it themselves, the earliest fragile beginnings of agriculture anywhere in the archaeological record. Sit with the shape of that idea for a moment, because I think it deserves more than a passing mention before we move on. If this interpretation holds even partly true, then the same abrupt climate swing that stalled an ocean current on one side of the planet may have helped push a handful of struggling communities on the completely opposite side of that same planet toward inventing farming. Not gently, not by choice, but out of the same kind of pressure that reshapes every stubborn, resourceful species eventually. Everything that grew out of that shift, permanent settlement, stored surplus, eventually writing cities and more or less the entire shape of human civilization. As we now understand, it may trace one of its earliest, most fragile threads directly back to a cold snap triggered by a lake in Canada, breaking through an ice dam and pouring itself into the wrong ocean. I'm not going to pretend that is a settled, proven fact, because it is not, and I distrust storytelling that flattens real ongoing scientific debate into something tidier than it deserves to be. Some archaeologists studying the same Natufian sites have pushed back hard against this narrative, pointing out that clear evidence of deliberate cultivation is thin on the ground during the Younger Dryas itself, and that the more dramatic shift toward true farming may not have arrived until conditions eased again afterward. The honest answer is that nobody currently has this fully settled, and I would rather tell you that plainly than hand you a neater story than the evidence supports. But even held loosely, even as one compelling thread among several competing explanations, it is hard not to feel something shift slightly in your chest when you hold it up next to everything else we have covered tonight. A tiny Arctic flower, patiently gathered from cold clay by a 19th century botanist. A flood that took 21 years to locate. And quite possibly somewhere in the middle of all that cold and difficulty, the first fragile seed of everything we now call civilization, planted by hands that had no idea they were doing anything more than trying to survive one more hard season. We have spent this member of the 25 looking at what this rhythm may have helped build a resilient people, push toward an entirely new way of feeding themselves, and by extension, all of us who came after. Which makes it worth asking honestly and without flinching what this same rhythm might have helped unmake much earlier, for a different group of people entirely who did not get nearly so fortunate an outcome, and who are no longer here to tell us their side of it. That is exactly where we are headed next. They were not who you think they were. If the word Neanderthal conjures up some hunched, grunting, not quite finished version of a human being dragging a club through a permanent grey winter, I would gently ask you to set that picture down for the next few minutes. it is by nearly every measure modern science can offer wrong. They controlled fire deliberately, not just opportunistically. They wore stitched hides against the cold. They cared for injured and elderly members of their own group, well past the point where such care offered any obvious survival advantage to the group as a whole. The kind of behaviour that looks from where we sit tonight remarkably close to tenderness. And the real story, the one written in ice and bone and a handful of stubborn cave floors, is a great deal more moving than the cartoon we inherited. Here is the fact that should stop you in your tracks before we go any further tonight. Neanderthals were already an established thriving presence across Europe and parts of Western Asia by roughly 350,000 years ago. Our own species, the one currently sitting here listening to a bedtime story about ice, has existed for a comparatively brief window next to that, and modern humans only began settling into Europe in any real numbers within the last fraction of that span. Which means Neanderthals did not experience one or two or even a handful of the abrupt swings we have spent this entire night tracing through Greenland's ice. They lived through dozens of them, entire cold plunges and sudden thaws arriving and retreating again, generation folding into generation, while a species we like to imagine as fragile and doomed simply kept adapting, kept hunting, kept surviving over and over for longer than recorded history could ever hope to measure. Let that sit with you for a moment. Whatever eventually happened to Neanderthals, it was not because a changing climate was somehow new to them. They were by any fair definition veterans of exactly this kind of chaos, seasoned in a way no other hominin species on the planet at that time could claim. If resilience alone were enough to guarantee survival, this is not a story that should end the way it does. So the real question tonight is not the lazy one most documentaries reach for the idea that a single harsh winter simply caught an unprepared species off guard. The real question is stranger and considerably more uncomfortable. If they had already weathered so many of these swings, what was different about the one that finally coincided with their disappearance? To answer that honestly, we need to look at the specific window of time in question a stretch scientists refer to by the rather dry label marine isotope stage 3, running roughly from 60,000 down to 25,000 years ago. If you have been following along with the pattern we mapped out earlier tonight, this stretch sits directly inside the most turbulent, densely packed section of the entire 25 event, record cold stadial and warm interstadial trading places again and again in relatively rapid succession, forests advancing and retreating across the continent almost within a single lifetime. Think of it as the single roughest patch of road on an already bumpy 100,000-year journey. The stretch where the swings arrived closer together and in some cases hit harder than almost anywhere else along the entire timeline. Picture what that actually meant on the ground for a family group moving through a forest in what is now southern France or northern Spain. A generation might grow up hunting red deer and wild boar in mixed woodland, learning the rhythm of a landscape that felt as far as anyone alive could tell, essentially permanent, the particular clearings where boar like to root in autumn, the river crossings deer favoured at dawn, knowledge passed down carefully from one generation of hunters to the next as though it would always hold true. Then within the span of a few decades that same woodland could thin into open steppe, the deer and boar shifting their range or vanishing from the area, entirely replaced by reindeer and horses better suited to colder, more open ground. Every single time this happened, it demanded an entirely different set of hunting knowledge, an entirely different sense of where water and shelter could reliably be found. Essentially a wholesale unlearning and relearning of the landscape within a single lifetime, and every single time the evidence suggests Neanderthal groups managed it, until around 40,000 years ago something else entered the landscape alongside them, And this is the moment where the story most people think they already know actually begins. This is the part of the story where I want to slow down and be honestly careful, because it is also the part where popular retellings tend to reach for the tidiest, most dramatic version of events, rather than the honest one. Homo sapiens began arriving in Europe in meaningful numbers around this same window, migrating up from the south and east, carrying a toolkit and a way of life researchers now group under the label Aurignation. And here is a detail that rarely makes it into the simplified version of this story. These early modern human populations do not appear to have simply marched into Europe whenever they pleased. The evidence suggests their major expansions tended to cluster during the milder interstadial stretches of the record, the exact same warm windows when the landscape briefly opened up and became easier to move through and survive on. Which means, for a difficult stretch of several thousand years, Neanderthals were no longer facing the old familiar problem alone. They were facing the same brutal swinging climate they had always weathered and layered directly on top of it. A resourceful, expanding, unfamiliar neighbour, arriving in exactly the windows when the landscape briefly had enough room and food to support extra mouths, and then contracting right back into fierce direct competition the moment the next cold stretch arrived and habitable land shrank again. Try imagining that rhythm for a moment, not as an abstract population graph, but as something a real family group would have felt directly. Good years arrive, and so unexpectedly do strangers. Hard years arrive again, and now there are more mouths than ever competing for the same shrinking hunting grounds those strangers once shared the good years with you. Here is a question worth sitting with honestly. Have you ever noticed how it is rarely one single hardship that breaks something? More often it is 2 or 3 ordinary pressures, each survivable completely on its own, arriving at exactly the same moment and refusing to let up. Scientists who study this period are, I want to stress, honestly divided on how to weigh these 2 pressures against each other, and I think that honesty matters more than a tidy conclusion would. Detailed habitat modelling of this exact period shows that during the coldest stadial stretches, the amount of land actually suitable for either species shrank dramatically and split into smaller scattered pockets, isolated from each other by belts of tundra, too harsh and too empty of game to cross safely, which on its own would have made life harder for Neanderthal populations regardless of who else was around. Some researchers working from that finding argue climate instability itself was doing most of the damage, squeezing population after population until the numbers simply could not recover between swings, each cold stretch chipping away a little more than the last warm stretch had managed to restore. Other research groups take a different approach entirely, building detailed computer simulations of both species moving and competing across the very same shifting landscape, tracking population numbers decade by decade under carefully varied assumptions. Run those models with the climate swings included but with no competing population present at all, and Neanderthal numbers dip and recover repeatedly battered, but never quite extinguished, much as they apparently had for hundreds of thousands of years before. It is only once researchers add an expanding resource-hungry neighbour into that same shrinking landscape that the population curve for Neanderthals tips decisively downward in the models and stays down, particularly in the more exposed reaches of northern Europe, where the 2 populations would have been pressed hardest into the very same dwindling patches of livable ground. I do not think either camp is being careless here. I think they are looking at the same violent, unstable stretch of climate history and reasonably disagreeing about how much weight to put on the shove climate provided versus the shove provided by sharing an increasingly crowded, unpredictable landscape with somebody new. Perhaps in the end that is even the wrong kind of question to insist on answering cleanly. Real populations rarely fail for one isolated reason that a single tidy paper can wrap up and close. They fail more often than not for several overlapping reasons at once, each one making the others slightly harder to survive. What almost everyone studying this period does agree on is where the story's last chapter played out. As conditions worsened further north, the final most resilient Neanderthal populations appear to have retreated toward the milder margins of the continent, holding on longest in the Iberian Peninsula, the southwestern corner of Europe, where the worst of the cold stadials bit somewhat less severely than they did further north, buffered a little by the Atlantic and the Mediterranean on either side. Some of the very latest confirmed traces of their presence come from cave sites along that southern coastline places, where a family could still find shelter, fresh water, and enough game to survive, even as the rest of the continent above them grew steadily less forgiving. It is a strange kind of comfort and a strange kind of sorrow, at the same time imagining an entire lineage, one that had outlasted dozens of these ancient climate swings already, finally being squeezed into a smaller and smaller corner of the map. It had called home for 300,000 years, right up until that last corner too eventually ran out of room. And yet here is where I think this story refuses to end quite as bleakly as it might first appear, and it is worth sitting with before we move on. Neanderthals did not simply vanish cleanly the way a species disappearing from a chart of extinction dates might suggest. In the years spent living alongside these newly arrived modern humans, sharing overlapping stretches of the very same landscape, we have just spent time picturing together the two populations occasionally had children. We know this today with the level of certainty nobody researching this question a generation ago could have dreamed of. A Swedish geneticist named Svante Perbo spent the better part of his career solving the almost impossibly difficult technical problem of extracting readable genetic material from bone that old, degraded and contaminated by everything that had touched it across tens of thousands of years, work that eventually earned him a Nobel Prize. His team's breakthrough allowed scientists to sequence an actual Neanderthal genome and compare it directly against the genomes of people alive right now. If you trace your ancestry outside of Africa, there is a real measurable chance that somewhere between 1 and 2% of your own genetic code did not come from Homo sapiens at all. It came from them. Sit with that for a second, because I think it quietly reframes everything we just talked about. Neanderthals were not simply erased by a shifting climate, outcompeted and left behind with nothing to show for 300,000 years of surviving exactly this kind of chaos. Some fraction of them at least became part of us. Every time you've ever pulled a blanket up against a cold night, some distant buried percentage of the genetic instructions doing that might trace back to a lineage that learned to survive Ice Age winters on this exact same shifting, treacherous continent long before anyone alive today existed to thank them for it. I find myself deeply moved by that more than by almost anything else we've covered tonight. It complicates the simple, satisfying story of a doomed species replaced by a superior one, and replaces it with something closer to the truth of how most endings in nature actually work: messy, partial, entangled rather than clean. Extinction, when you look closely enough at almost any real example of it, rarely arrives as a single door slamming shut. More often it looks like this: several separate pressures leaning on the same population at once, some of that population's traits and knowledge and even genes quietly slipping sideways into whoever happens to survive them, so that no line ever gets drawn quite as cleanly as our history books would prefer. I suspect that is true of a great many endings well beyond this one in nature and in our own lives alike. Less a single slammed door and more a slow handing off of pieces to whatever comes next. We have now spent a great deal of tonight trusting numbers pulled from single tubes of ancient ice, trusting that a jagged line on somebody's graph really does represent a hemisphere's worth of ancient suffering and adaptation, trusting extinction models and habitat maps built by scientists none of us will ever meet. Which raises a perfectly fair question, one I think you deserve a proper answer to before we go any further. How do scientists actually know any of this holds up? Not just once, not just from one lucky core pulled from one lucky spot in Greenland, but as something solid enough to build an entire understanding of the ancient world, upon solid enough to hang a story about an entire vanished lineage on. That is exactly where we are headed next. Science has a rule that sounds almost impolite when you say it out loud. Do not fully believe anything, no matter how elegant it looks on paper, until somebody else working completely independently digs up the exact same answer without knowing what you already found. It is a slightly uncomfortable standard to hold yourself to. Imagine spending 5 years of your life on a single research project, only to treat your own hard-won result as provisional incomplete, not quite trustworthy yet, until a total stranger on the other side of the world manages to stumble onto the same conclusion by an entirely different path. Most of us in our own lives do not operate that way at all. We believe something the moment it feels true to us, the moment it fits the story we were already inclined to tell ourselves. Science, at least in its best moments, insists on something harder and considerably less flattering to the ego. And yet that stubborn, slightly humbling rule is exactly what turned everything we have spent tonight discussing from an interesting hypothesis into something close to bedrock certainty. Let me show you what that actually looked like in practice, because the story itself has more suspense in it than I think it gets credit for. By the late 1980s, the scientific reputation of Willy Dansgaard's original discovery rested on a slightly uncomfortable foundation. A single deep ice core pulled from underneath a military base had suggested Greenland's climate once swung wildly and repeatedly. A second core at Die 3 had backed that up. But 2 cores drilled reasonably close together on the very same ice sheet were still, in the strictest scientific sense, only 2 witnesses to the same event. If you wanted to settle the matter permanently, you needed something closer to a controlled experiment. You needed 2 entirely separate teams working independently, without comparing notes along the way, drilling 2 entirely separate holes into the ice, and then only at the very end opening up their results side by side to see whether they agreed. That is essentially what happened next, although not entirely on purpose. A European consortium built largely out of the collaboration Dansgaard himself had spent years assembling. After political circumstances made continuing his earlier American partnership impossible, began drilling at the highest point of the Greenland ice sheet in 1989. They called their effort the Greenland Ice Core Project. At almost the very same time, separately funded and separately organized, an American team backed by the National Science Foundation began drilling their own deep core roughly 30 kilometers away, close enough to share the same weather, the same snowfall, essentially the same patch of ice sheet, but organizationally about as independent as 2 teams working that close together could possibly be. Different funding sources, different drilling equipment, different laboratories waiting back home to analyze whatever ice eventually came up. By deliberate design, and by more than a little healthy competitive pride on both sides, neither team spent those years comparing raw numbers with the other while the drilling was underway. They called their effort the Greenland Ice Sheet Project 2. Here is a question worth pausing on before I tell you what happened. If you were designing an experiment specifically meant to test whether Dansgaard's original discovery could be trusted, could you have built a fairer one than this? Both drilling efforts took years. Both eventually reached all the way down to bedrock more than 3 kilometers beneath the surface, pulling up ice older than the last several ice ages combined. And then came the moment every scientist involved must have been quietly dreading and anticipating in equal measure the moment to finally compare notes. For the entire span of the last glacial period, the very stretch of time we've spent this whole night exploring, together the two records matched beautifully. Not roughly, not loosely. The same abrupt jumps, the same slow slides back into cold, the same overall rhythm showing up independently in ice drilled by two different countries using two different drills, analysed in two different laboratories by two teams of scientists who had not been comparing their raw data as they worked. 25 swings more or less exactly where Dansgaard's original core had suggested they would be down, to details neither team could have simply guessed their way into matching by coincidence. It is hard to overstate how significant that moment was. An anomaly discovered by one determined man in Copenhagen decades earlier had just been independently unknowingly confirmed by an entirely separate team working a short walk away. I want you to sit with that feeling for a second because I think it is worth savouring before I complicate it. That is what it looks like when a wild, unbelievable discovery survives its hardest test. But science done honestly rarely lets you enjoy a clean victory for very long, and this story is no exception. When both teams pushed their comparison deeper still past the last ice age into the older layers, representing the previous warm interglacial period, a stretch of climate history sometimes called the Eemian, something went wrong. The two cores stopped agreeing with each other. One record suggested the Eemian, a warm period not entirely unlike the one we are living through right now, had been shockingly unstable, swinging wildly in ways that would be alarming if true of our own current climate. The other core, drilled barely 30 kilometers away, showed something calmer, closer to the gentle stability most scientists had always assumed an interglacial period ought to have. Two supposedly identical experiments run on the very same mountain of ice had somehow returned two contradictory verdicts about the exact same stretch of ancient time. Can you imagine the particular flavour of unease that must have settled over that research community? Not doubt about whether abrupt climate change was real, that part had just been beautifully confirmed. But a much more unsettling question. Were even warm, comfortable periods like our own secretly capable of the same kind of violent swings? And if two nearly identical cores could not even agree on the answer, how would anyone ever know for certain? It took years of careful patient detective work to sort out what had actually gone wrong, and I think the eventual answer says something important about the limits of even the best available evidence. Deep down near bedrock ice behaves very differently than it does near the surface. Under that much accumulated pressure squeezed between the weight of an entire ice sheet above and the uneven rocky ground below the oldest layers, can folds stretch, and occasionally overturn entirely the geological equivalent of a neatly stacked deck of cards getting dropped and reshuffled slightly on its way to the floor. A layer that formed early might end up folded back on top of a layer that formed later, and from the surface, sliced open in a laboratory, thousands of kilometers away, there is no obvious way to tell that the deck has been shuffled at all unless you know exactly what subtle signs to look for. Scientists eventually confirmed, through careful study of ice crystal structure and subtle visual banding, invisible to a casual glance, faint clues in how the ice crystals themselves had been physically bent and reoriented under strain that both deep cores had likely been physically disturbed near their very bottom, scrambling the true order of the ancient layers just enough to produce two different, equally unreliable stories about the same real period of history. The instability was not necessarily fiction entirely. Some later more careful evidence has suggested a milder version of Eemian variability may truly exist. But the wild dramatic swings either core seemed to suggest on its own turned out to be at least in significant part an artifact of disturbed ice, rather than a faithful record of ancient weather. I find something quietly reassuring in that outcome, even though it sounds on its face like a story about science getting something wrong. Because what actually happened was scientists noticing a disagreement, refusing to simply pick whichever answer they liked better, and instead spending years digging into why two respected, carefully gathered records could disagree at all. That is not a failure of the method. That is the method working exactly the way it is supposed to. And here is the detail that matters most for everything we have spent tonight building together. The part of the record that mattered for our story, the 25 abrupt swings of the last glacial period, was never the part in question. That part held up cleanly, consistently, confirmed independently by two teams who were not looking over each other's shoulders while they worked. Still, I think it is fair to ask for more than just two witnesses standing 30 kilometers apart on the very same mountain of ice. So let me take you somewhere considerably further away to a limestone cave outside Nanjing, in eastern China, where an entirely different kind of scientist using an entirely different material, an entirely different dating method, and an entirely different climate signal altogether ended up telling us almost exactly the same story. Picture the setting for a moment, because it could hardly be further removed from a windswept Greenland summit. No snow, no drilling rig, no Parker. Just a quiet, dripping darkness water finding its way down through cracks in the limestone above mineral by mineral, one imperceptible layer at a time over tens of thousands of years, building slender columns of stone rising up from the cave floor toward a ceiling nobody had bothered to disturb since long before the last ice age ended. Inside Hulu Cave, water dripping slowly from the ceiling over tens of thousands of years has built up columns of solid mineral called stalagmites, growing upward from the cave floor one thin mineral layer at a time. Unlike ice, which requires counting individual yearly layers back through time, these mineral deposits carry their own built-in clock, a tiny, steadily decaying trace of uranium locked inside the stone the moment it formed, converting into thorium at a rate physicists understand with extraordinary precision. Measure that ratio at any point along the stalagmite, and you get a date not estimated, not counted, but calculated, directly from the reliable arithmetic of radioactive decay, completely independent of anything happening thousands of kilometers away on a Greenland ice sheet. What those stalagmites actually recorded was not temperature at all, but rainfall, specifically the strength of the East Asian summer monsoon, the seasonal rains that sweep in off the ocean and determine whether an entire region's crops succeed or fail in a given year. When that monsoon runs, strong oxygen isotopes in the rainwater feeding the cave carry one particular signature. When it weakens and falters, that signature shifts measurably in the other direction, locked permanently into whatever thin layer of mineral happens to be forming at that exact moment. And when researchers led by a geochemist named Yongjin Wang, working alongside American colleagues, lined up the monsoon record hidden inside that cave against the temperature record hidden inside Greenland's ice, the two matched with startling precision. Strong monsoon seasons in China lined up with the warm, interstadial swings in Greenland. Weak, faltering monsoons lined up with the cold stadials. The same 25 heartbeat rhythm recorded independently on the opposite side of the planet by a completely different climate system, using a completely different material dated by a completely different clock. Think about what that actually requires for a moment. A scientist in a laboratory in Copenhagen and a scientist in a laboratory outside Nanjing working decades apart studying entirely different substances, arriving at the exact same underlying rhythm without either one setting out to confirm the other. That is not the kind of agreement you get by accident, and it is not the kind of agreement you get from a single flawed method, fooling everyone the same way. A shared mistake in how ice cores are dated might explain away one strange match. It cannot explain why cave stone dated by an entirely unrelated branch of physics keeps landing on the very same numbers. When your two most different possible witnesses, ice from the top of the world and stone from a cave on the other side of it, sit down and tell you the identical story, you stop treating that story as a hypothesis and start treating it as something considerably closer to fact. I keep coming back to how strange and moving that is, honestly. Two utterly unrelated corners of the planet, an Arctic ice sheet and a cave full of dripping limestone, somehow ended up keeping the very same diary in two entirely different kinds of ink, without either one knowing the other existed. There is something almost tender about that image if you let yourself sit with it. The planet, it turns out, was quietly writing the same story in more than one language at once, and it simply took us a very long time to learn how to translate more than one of them, which raises a question I think deserves its own place in tonight's story before we go much further. If a rhythm born somewhere in the North Atlantic could reach far enough to rewrite the rainfall patterns of an entire Asian monsoon season thousands of kilometers away, what else did it reach along the way? How far did this heartbeat actually travel before it ran out of world to touch? That is exactly where we are headed next. The answer, it turns out, is almost the entire planet. Let's start at the farthest possible point away from Greenland you could reasonably choose, the icy storm-scoured plateau of Antarctica, sitting at the opposite end of the Earth, separated from the North Atlantic by an entire globe's worth of ocean and equator and everything in between. If this rhythm really was a local regional event confined to one corner of one hemisphere, the way a passing storm stays confined to whichever coastline it happens to strike, Antarctica should have had nothing whatsoever to say about it. Antarctica had quite a lot to say about it. In the early 2000s, a European team working under a project called the European Project for Ice Coring in Antarctica drilled a careful high-resolution core in a region called Dronning Maudland, a site chosen deliberately rather than conveniently specifically, because its position facing the South Atlantic gave it the best possible chance of picking up any signal connected to the very same ocean circulation we spent time understanding earlier tonight. The drilling itself was every bit as grueling as anything we have already described happening in Greenland teams working through Antarctic field seasons in temperatures that make a bad winter back home look almost pleasant by comparison. When researchers finally lined that Antarctic record up against the Greenland ice cores, matching them year for year using shared markers like volcanic ash and trapped methane bubbles that both hemispheres would have absorbed from the same well-mixed atmosphere at essentially the same moment, something remarkable emerged. Every single one of the 25 abrupt Greenland swings had a mirror image buried in the Antarctic ice. Not identical. Gentler, slower, stretched out rather than sudden, but unmistakably present every time without exception. Here is the part that still catches me off guard every time I think about it. The two records were not simply matching, they were running in opposite directions. When Greenland plunged abruptly into one of its cold stadials, Antarctica, thousands of kilometers away on the far side of the planet, began warming slowly and steadily, as though the two poles were seated on opposite ends of a very long, very slow seesaw. And when Greenland finally snapped back into a warm interstadial Antarctica, right on schedule, began cooling again. Scientists gave this pattern a name that captures the image perfectly. They call it the bipolar seesaw. Have you ever pushed down on one end of a real seesaw and felt almost instantly the other end lift without you touching it directly? That is essentially the physical intuition behind what was happening here, except stretched across an entire hemisphere and playing out over centuries rather than seconds. The mechanism, once you already understand the ocean engine we spent time tracing earlier, is almost elegant in its simplicity. That great circulating system does not just move heat around within the North Atlantic, it is part of a truly global loop, and heat, like water finding the fastest path downhill, tends to pool wherever it is not actively being pulled away. When the circulation runs strong, it drags warmth up out of the southern oceans and delivers it directly to Greenland's doorstep, which is part of why the North warms so abruptly during an interstadial. But that heat has to come from somewhere. Pulling it northward means the southern hemisphere loses a little of what it would otherwise have kept for itself, and Antarctica cools. Reverse the process, stall the circulation during a stadial, and that same heat, no longer being hauled north, simply stays put in the south instead, and Antarctica slowly warms. In effect, the two poles are not experiencing two separate climate stories at all. They are sharing a single fixed budget of heat, and whichever pole happens to be losing the tug of war in a given century pays for it directly out of the other one's pocket. Wallace Brucker, the very scientist whose ocean engine we spent considerable time with earlier tonight, was actually the first to propose this exact mechanism. Back in 1998, sketching out on paper the idea of a seesaw balanced across the equator years before the ice core evidence existed to properly confirm it. It is worth pausing on that for a moment. He guessed correctly about a pattern buried in Antarctic ice that nobody had even drilled, yet reasoning his way to the answer from the physics of heat and salt water alone, long before anyone could hand him the data to check his work against. That is in its own quiet way just as impressive as anything a drilling team accomplished with picks and augers and years of frozen fieldwork. Researchers have since worked out the seesaw's timing with impressive precision. Antarctica does not respond instantly. The warming or cooling down south tends to lag behind whatever just happened in Greenland by somewhere in the neighbourhood of 2 centuries, roughly 200 years for the message carried entirely by ocean water, rather than any signal moving through the air to complete its journey from one pole to the other. Picture that delay for a moment. An abrupt shift begins in the North Atlantic, and the news of it, so to speak, does not reach the opposite end of the Earth until 200 years later, an ocean current serving as the slowest possible postal service imaginable, delivering the same message to every mailbox on the planet, just on wildly different schedules depending on how far away that particular mailbox happens to sit. If the poles themselves were listening to this rhythm, I think it is worth asking what else within reach of the tropics might have been listening to. And this is where the story turns from oceans and ice towards something considerably warmer and considerably more directly tied to the fate of people. Picture the Sahara not as it exists today, but as satellite dust records and ancient lake sediments suggest it periodically became during the warmest of these interstadial swings. Today's Sahara is the largest hot desert on the planet, an unforgiving stretch of sand and rock that has claimed the lives of travellers for as long as anyone has attempted to cross it, a place where a single wrong turn can still mean death by thirst within a day or two. But the desert you would recognise today is not a fixed, permanent feature of the African continent. It is something closer to a slow-breathing border expanding and contracting across tens of thousands of years, tracking the same rhythm we have spent this entire night learning to recognise. Here is the mechanism, and I promise it connects directly back to everything we already understand. A broad band of intense tropical rainfall meteorologists call it the Intertropical Convergence Zone, drifts north and south across the equator over the course of each year following the sun. During the warmest interstadial swings, that rain belt appears to have pushed unusually far north, dragging the West African monsoon along with it deep into territory that sits bone dry today. Lake Chad, a modest shrinking body of water in our own era, one you could walk most of the way around in an afternoon in a bad year, now appears to have swollen at these moments into something enormous, by some estimates rivaling the size of the Caspian Sea, an inland sea, sitting where herders today struggle to water a handful of cattle. Rivers that are nothing more than dry, cracked wadis today ran with actual water year-round, reliable enough to support fish and hippopotamus and crocodile alongside the people who hunted them. Grasslands and scattered woodland spread across what is now empty dune, and gravel plain rock art still visible today across the central Sahara, depicting swimmers, cattle herds and giraffe in places no giraffe could survive for a single afternoon now. Researchers studying dust records pulled from marine sediment off the African coast can watch this happen, almost in real time geologically speaking. Ocean floor mud downwind of the Sahara acts as a kind of atmospheric weather diary, catching and burying whatever dust the desert happened to be throwing into the sky. In any given century, more dust during dry, barren stretches, dramatically less during the rare windows when vegetation held the soil in place instead. Around 14,500 years ago, precisely the same interstadial swing that we've already met tonight, under its more familiar name, the Bulling Alarud, the dust pouring off the Sahara into the surrounding ocean, suddenly dramatically drops exactly the kind of signature you would expect if a howling desert had briefly turned green. Can you picture what that would have meant for anyone standing in the middle of it, watching a desert quietly become a savanna within the span of a single lifetime? For the plants and animals native to Africa, a green Sahara functioned as a corridor rather than a barrier, an open highway stretching from the heart of the continent up toward the Mediterranean coast and the land bridges leading into the Middle East and beyond. Species that could never have crossed a true desert suddenly found the way open. And when the interstadial ended, when the rain belt inevitably slid back south and the desert reasserted itself, that corridor slammed shut again just as abruptly as it had opened, splitting populations on either side of a landscape that had briefly generously let them mingle, and then just as quickly changed its mind. I want you to sit with the scale of that idea for a moment, because I think it deserves more weight than a passing mention. Researchers studying the deep history of human migration out of Africa have pointed to these exact green Sahara windows as plausible corridors for some of our own ancestors' earliest journeys northward, entire population movements potentially made possible, or made impossible, by whether an ocean current on the far side of the world happened to be running strong or running weak in that particular millennium. Whole branches of the family tree we all eventually belong to may have taken the shape they did simply because a corridor happened to be open or closed at the exact moment a small group of people needed it most. This is, I think, one of the most quietly staggering ideas in the whole story we've built together tonight. A change in salinity in the cold water off the coast of Greenland, invisible, silent, entirely disconnected from anything a person standing in North Africa could ever have perceived directly, may have reached all the way down across an entire continent and either opened or closed the very route some of our ancestors eventually used to leave it. Nothing about that connection would have been obvious to anyone living through it. Nobody standing beside a newly flowing river in what should have been desert would have had any reason to suspect that the true cause sat thousands of kilometers away, at the bottom of a cold, dark ocean most of them would never see or even hear described. There was no thunder to hear, no visible sign in the sky, nothing a person could point to and say, "There, that is what changed my world." And yet the connection was real, physical, traceable today in dust layers and drowned lake beds, and as we already spent time discovering in the very same rhythm, recorded independently inside a cave in China. I keep returning to this thought whenever I sit with tonight's story as a whole. We tend to imagine cause and effect as something that happens nearby, a hand pushing directly against whatever moves. This entire season of climate history keeps insisting on something stranger and considerably more humbling, that a single quiet shift in one unremarkable stretch of ocean could ripple outward across an entire planet, reshaping rainfall in Africa, monsoons in Asia, and the very temperature of the opposite pole, all without a single one of those distant places ever being touched directly by whatever set the whole chain of events into motion. Have you ever traced a hard moment in your own life back far enough and found the true origin sitting somewhere you never would have thought to look a decision made by someone you never met in a place you've never been years before it ever reached you? I think that is a very human feeling, and I think it is also in its own strange way a planetary one. If a shift that quiet could reach that far into deserts and monsoons and the opposite pole of the Earth, it raises an uncomfortable question we have mostly avoided until now. Every single time we've discussed one of these 25 swings tonight, we have discussed it as something that already happened, safely finished sealed inside ancient ice. But the mechanism behind it, the ocean engine, the fragile point where fresh water meets salt water, at exactly the wrong moment has not gone anywhere. It is still down there right now doing exactly what it has always done. That is exactly where we need to go next. Could anyone have seen it coming? Not after the fact, not from the safety of a laboratory decades later, with the whole graph laid out in front of you, every jump already labelled, dated and explained. I mean in the moment standing inside the actual unfolding decade with no idea what came next. If you had been standing in Greenland several centuries before, one of these 25 swings finally arrived, watching the seasons come and go with what felt like perfect, boring reliability. The same hunting grounds, the same rough rhythm of snow and thaw. Your grandparents had also known, was there anything at all hidden in the pattern of those seemingly ordinary years that might have quietly told you a jump was coming? That question has occupied a very particular, very stubborn corner of climate science for the better part of 2 decades now, and I want to walk you through it carefully tonight, because I think it might be the closest thing this whole story has to a genuine, unresolved cliffhanger, one that is still being actively argued over in journals as recently as this year. Here is the idea underneath it, and it comes from a branch of physics and mathematics that has almost nothing to do with climate on the surface. Imagine a marble resting at the bottom of a wide, deep bowl. Give that marble a little nudge, and it rolls a short way up the side before rolling right back down to rest exactly where it started. The deeper and wider the bowl, the faster that marble settles back into place after any small disturbance, and the harder it is to knock it out entirely. You could nudge it a dozen times a day and never worry about it actually escaping. Now imagine very slowly, without the marble noticing, that the bowl itself is flattening, growing shallower, wider at the base, but with less and less of a real slope to hold the marble in place. The marble still looks perfectly settled from a distance, still sitting quietly at the bottom, still returning to more or less the same spot after each little nudge. Nothing about its resting position has visibly changed at all, but if you timed exactly how long it took to settle back down after each disturbance, patiently nudge after nudge, year after year, you would notice something. It is taking longer. A little longer after this nudge than the last one, longer still after the one after that. The system in the language mathematicians use for this is slowing down, critically becoming sluggish in its recovery, precisely because the safe, stable bowl holding it in place is quietly losing its grip. Eventually the bowl flattens out so completely that even an ordinary, unremarkable nudge, nothing special, nothing dramatic, the kind of nudge it would have shrugged off 1,000 times before without incident, is enough to send the marble rolling entirely out of the bowl and into a completely different resting place. Scientists suspect something remarkably similar might have been happening inside the North Atlantic Ocean system in the centuries leading up to several of these 25 swings. Not a marble, of course, but the same underlying mathematics, as the ocean circulation crept closer to whatever invisible threshold eventually sent it tipping from one stable state into another. The whole system may have grown measurably slower and wobblier in how it recovered from the ordinary everyday disturbances. Every climate system absorbs constantly a passing volcanic eruption, an unusually snowy winter, small fluctuations that come and go without incident most of the time. There is a reasonable guess about what might have actually been losing its grip underneath all that trembling, and it involves a part of the system we have not spent much time with tonight: sea ice. Floating sea ice does something deceptively important for the whole northern climate, reflecting sunlight straight back into space, rather than letting the darker ocean water beneath it soak that heat in. As the system edges closer to a tipping point, some researchers suspect the sea ice edge itself becomes increasingly unstable, first flickering, retreating and reforming more erratically than usual, a kind of restless twitching at the very front line of the system, before the deeper ocean circulation underneath it ever visibly commits to reorganizing. If that is right, the sea ice may have been the nervous, jittery early responder, and the great ocean engine the slower, heavier machinery that only finally lurched into motion once the twitching out front had gone on long enough. If that idea holds true, it would mean something rather remarkable. It would mean the ice itself might be quietly recording not just when these swings happened, but whether nature was in some meaningful sense leaning toward one before it actually arrived. In 2018, a researcher named Niklas Boers set out to test exactly that idea, combing back through the extraordinarily detailed high-resolution ice core data drilled at the summit of the Greenland ice sheet. He looked specifically at the centuries leading up to several of the abrupt jumps we've already spent tonight getting to know, searching for precisely the fingerprints that theory predicted: growing wobble, growing memory in the noise, the statistical equivalent of that marble taking longer and longer to settle. This was not simple work. The signal he was hunting for, if it existed at all, would be buried underneath decades of ordinary seasonal static snow year, piled on snow year, most of it, meaning nothing more than the ordinary business of weather. And in a meaningful number of cases he found what he was looking for anyway. The signal was faint, easy to miss if you were not looking with exactly the right statistical lens, but it appeared to be there. A quiet trembling in the ice in the centuries before several of the biggest jumps in the entire record. Can you imagine what it must feel like to comb through data frozen for tens of thousands of years and find something that looks uncannily like foresight evidence that the system itself seemed to know in some purely physical sense what it was about to do decades or even centuries before the ice ever registered the actual jump? For a while, this felt like one of the most exciting frontiers in the entire field. If ancient ice held genuine detectable warning signs before a major climate tipping point, the same statistical tools might eventually be pointed at our own living, breathing climate system today, potentially offering something close to an early alarm before a modern tipping point ever arrived. It is the kind of finding that understandably makes headlines the sort of result that gets quoted in policy briefings and cited in urgent warnings, because if it holds up, it hands humanity something truly rare, where climate risk is concerned, an actual testable early warning light on the dashboard, rather than a vague sense of unease about the future. But I promised you honesty over tidiness tonight, and this is exactly the point in the story where honesty demands a pause. Earlier this year, a fresh, more rigorous look back through that same evidence involving Boers himself, alongside colleagues willing to test his own earlier work, arrived at a noticeably more cautious conclusion. The team went back through the same ice core records with sharper statistical methods, checking whether the original warning signals could survive being compared against a much wider range of possible false alarms, essentially asking whether a similarly noisy, but entirely random sequence of numbers might produce the same kind of apparent trembling purely by chance. Using those sharper tools and testing the results against that wider set of possible false alarms, the team found meaningfully fewer of these warning signals holding up under closer scrutiny than the original analysis had suggested. Some of the trembling that once looked like foresight may simply be the ordinary expected noise of a truly chaotic system, the climate equivalent of hearing a pattern in television static because you were already primed to expect one. I find that entirely admirable, honestly, and I want to sit with it for a moment rather than rushing past it. A scientist built a career finding an idea exciting enough to reshape how an entire field thought about predicting climate tipping points, and then turned around years later and helped test whether his own earlier conclusion could survive tougher scrutiny. It did not survive entirely intact. He said so plainly in print under his own name. Have you ever had to be the one to quietly walk back something you were once truly excited about simply because closer honesty demanded it? It is a particular kind of integrity that rarely gets celebrated the way a bold new discovery does. Nobody writes an exciting headline about a scientist finding fewer warning signals than expected. There is no dramatic photograph, no thrilling press release, no easy way to make caution sound as exciting as certainty. And yet, I think it deserves celebrating anyway, maybe even more than the original finding did, because it is considerably harder to do. So where does that leave the actual question we started with tonight? Could anyone have seen one of these swings coming? The honest answer right now, sitting exactly where the research currently stands, is a genuine maybe. Some swings in the record do appear to carry a faint statistical shadow beforehand, a system audibly slowing down before it finally tips. Others show nothing detectable at all, arriving as abruptly to careful statistical analysis as they must have arrived to anyone unlucky enough to be living through one no warning, no trembling, just a sudden complete reorganization of the world within a matter of decades. It may simply be that not every tipping point announces itself the same way. Some systems creep slowly toward the edge of a flattening bowl, exactly the way we just pictured together. Others might get pushed over an edge that was never gradually eroding at all, shoved rather than slid by something sudden and external, a particularly large volcanic eruption, an unusually large pulse of meltwater arriving all at once, rather than something building quietly from within over centuries. Mathematicians studying this distinction have even started giving the different flavors their own names, separating tips caused by a slowly eroding threshold from tips caused simply by how fast an external push arrives, regardless of how stable the underlying system otherwise remained. I think there is real wisdom hiding inside that uncertainty if you are willing to sit with it rather than demand a tidier answer than the evidence currently supports. We would all love to believe every serious danger announces itself in advance, gives us a gentle, detectable tremor before the real shaking begins enough notice to prepare to brace, to make different choices, while there is still time to matter. Sometimes that seems to be true. The ice, at least in places, appears to remember growing unsteady before it finally gave way. But sometimes, honestly, warnings simply are not there to find, no matter how carefully or how patiently anyone looks for them. Some doors shut without ever creaking first. Here is why none of this stays safely confined to the deep past, and why I think it deserves your full attention, rather than a passing mention before we close things out tonight. The very same statistical toolkit Bohr's built to search ancient ice for early tremors has already been pointed somewhere considerably closer to home, at today's actual ocean circulation, at the very same fragile salt-dependent engine We spent real time understanding earlier tonight the one currently still running right now beneath the surface of the North Atlantic, while you listen to this in whatever quiet room you happen to be in tonight. This is not a hypothetical exercise anymore, and it is not confined to a graph representing 100,000 years of frozen history. Actual oceanographers using actual instruments lowered into actual water this year are asking the exact same question about the exact same current, and the answer, whatever it turns out to be, will not stay locked away in a laboratory. It will eventually shape decisions made by people who plan coastlines and harvests and entire national economies decades into the future. What those more recent measurements seem to be showing is a conversation I think deserves its own space to unfold properly, rather than a rushed final thought squeezed in at the very end of tonight's story. That is exactly where we are headed next, somewhere in the middle of the Atlantic Ocean right now while you are lying there listening to my voice. A scattered chain of scientific instruments is quietly doing something Willy Dansgaard could only have dreamed of on that snowy Copenhagen night we started with. Sensors anchored to the seafloor, strung up along cables stretching between the coast of Florida and the coast of Africa, are measuring continuously, in real time, the strength of the very same ocean engine we've spent this entire night learning to understand. Scientists call this particular network the Rapid Array, and it has been sitting quietly in the water since 2004, patiently logging the pulse of the Atlantic, the way a nurse might keep a permanent finger on someone's wrist. Moorings anchored to the ocean floor rise up through miles of dark water, each one carrying sensors that measure temperature, salt content, and the speed of the current passing by, all of it beamed back to researchers who no longer have to guess at the health of this system from a handful of scattered ship visits decades apart. For the first time in the whole history of this science, nobody has to wait for a research vessel to happen to sail through, and nobody has to drill through a mile of ice and wait months for laboratory results. The ocean is being listened to directly continuously, the moment history is being made rather than centuries afterward. And what that listening has picked up these past few years is not exactly comforting. South of Greenland and Iceland, in a patch of the North Atlantic that oceanographers now simply call the cold blob, something truly strange has been happening. While nearly every other stretch of ocean on the planet has been steadily warming, this one particular region has been doing the opposite, cooling quietly and stubbornly, even as the water all around it climbs. Nobody standing on a beach anywhere near there would necessarily notice anything unusual, and the difference in temperature we're talking about is not the kind that would ruin a swim. But viewed from above in satellite temperature maps built up year after year, that cold patch sits there like a bruise that refuses to fade, exactly the kind of pattern you would expect to see if the warm water normally delivered to that region by the ocean engine were arriving in smaller amounts than it used to. Is that patch of unusually cold water an early tremor, the same kind of warning sign we spent time exploring together only moments ago, or is it simply an unrelated quirk of ordinary ocean weather that happens to be sitting in an unfortunate spot? Honestly, right now, serious researchers disagree, and I think you deserve to hear that disagreement laid out plainly, rather than flattened into false certainty in either direction. One major study published last year, built on refined ocean physics and real measurements gathered from that same rapid array, concluded the circulation is likely to weaken over this century, meaningfully uncomfortably, but probably not collapse outright even under a future of continued heavy emissions. A full shutdown within our own century by that particular analysis looks unlikely, and the researchers behind it were careful to say, so plainly resisting the temptation to sensationalize a result that honestly called for restraint. Other researchers working from a different angle, entirely applying the same statistical tools we discussed a little while ago, the ones built originally to search ancient ice for warning tremors, have reached a considerably more urgent conclusion, estimating that current trends could push the circulation toward an actual collapse sometime around the middle of this century, well within the lifetime of most people listening to this tonight. Between those two positions sits a wide, uncomfortable range of other careful estimates, some pointing toward a slow, manageable decline stretched out over centuries, others warning the threshold could be considerably closer than most people assume. This is not a case of one lone alarmist against a chorus of calm experts or the reverse. It is a genuine ongoing disagreement among people who have devoted their careers to getting the answer right. And this year a separate team modelling what would actually happen if that collapse ever did occur added a detail that I think deserves to sit with you a little longer than the rest. Their work suggests that once the circulation crosses that particular threshold, it may not simply switch back on again once conditions improve the way you might hope a stalled engine eventually restarts on its own once the weather clears. It may stay off essentially permanently for as long as carbon dioxide levels in the atmosphere remain above a certain threshold, a threshold considerably lower than where we already stand today. Not a pause, not a temporary dimming that fixes itself once emissions eventually come back down. A door that once it swings shut may simply refuse to swing back open again on any timescale that matters to the people currently alive to worry about it. I want to be honest with you about what that specific detail means and what it does not mean. It does not mean scientists have agreed collapse is coming. Plenty of serious, careful people remain honestly unconvinced that a full shutdown is likely this century at all. What it does mean is that if the more cautious voices turn out to be wrong, the ones warning of a nearer, faster tipping point, there may not be a simple way to undo it afterward. It is the kind of asymmetry that tends to make careful people more careful rather than less even amid real uncertainty. It is worth knowing too that this conversation has already stepped outside academic journals and into rooms where actual decisions get made. Iceland's government formally described a weakening circulation as a matter of national security in the past year, an unusually blunt phrase for a topic that used to stay almost entirely inside climate conferences. A council representing the Nordic countries published a joint assessment earlier this year, urging stronger long-term monitoring and preparation, treating the question less like a distant hypothetical and more like a slow-moving possibility worth taking seriously starting now, whichever way the science eventually settles. None of this means the outcome is decided. It simply means the people whose job it is to plan decades ahead are no longer willing to file this question away as purely theoretical. Can you feel the strange symmetry sitting underneath all of this? The same one I have been circling back to all night without quite naming it directly until now. Willi Dansgaard sat alone in a quiet room decades ago, staring at a strip of paper, trying to convince himself that an impossible jump on a graph was actually real, checking and rechecking a single stubborn number until he trusted it enough to believe it. Tonight, an entire international community of oceanographers, glaciologists, and climate physicists is doing something remarkably similar, staring at real-time data streaming up from the bottom of the same ocean, cross-checking each other's numbers the way Dansgaard once cross-checked his own, trying to work out whether the very same switch that flipped 25 times across the last ice age might be edging toward flipping once again. The instruments have changed almost beyond recognition. The basic human posture leaning in close, refusing to look away, checking the impossible number one more time before believing it has not changed at all. This time, though, it is not a scattering of hunters following reindeer across an empty tundra standing in the path of whatever comes next. It is almost 8 billion people in cities and coastlines. This entire mechanism was never designed with in mind. That more than any single fact or figure is what I hope stays with you after tonight. This was never simply a story about the deep past. It only ever felt that way because the deepest parts of it happened to be finished already safely sealed inside ice, old enough to feel like myth. The mechanism itself was never resting. It was only ever waiting. Let's gather up everything we have carried through this long, strange night together, because I think it deserves one last look before we let it go. We started with one stubborn man in a cold laboratory, refusing to believe his own eyes until he had checked the impossible number 3 times. We learned that the world he was reading about had never been the slow, sleepy place the textbooks promised, but something closer to a heartbeat, 25 times over, hidden in frozen snowflakes and ancient air. We met the people who built the instruments patient enough to hear it, a Swiss physicist who once dreamed of being a musician, a geochemist raised to believe the Earth was only a few thousand years old, who ended up mapping processes tens of thousands of years deep, a German geologist who found rocks where no rocks should ever have been. We watched an ice sheet quietly build pressure against itself for millennia before letting go all at once, and we watched 2 separate teams of scientists working 30 kilometers apart argue honestly when their own results disagreed with each other rather than simply picking whichever answer flattered them more. We traced this same hidden rhythm as it reached into deserts and monsoons and the coldest edges of the opposite pole further than anyone standing inside any single one of those moments could possibly have guessed. And we sat gently and honestly with 2 very different peoples who lived through versions of this same story. One whose desperate resourcefulness may have helped invent farming and eventually everything we now call civilization, and one that after 300,000 resilient years of surviving, exactly this kind of chaos quietly became part of us, instead of simply ending carried forward today in a small buried percentage of nearly all our own genetic code. If there is a single thread running underneath all of it, I think it might be this. The world has never been as settled as it looks on a calm evening. Not the ancient world we spent tonight exploring, and if the scientists listening to that ocean right now are right to be even a little bit worried, perhaps not the one waiting for you tomorrow morning either. That is not meant to frighten you before you shut your eyes. I think it is meant to do almost the opposite. Every single person we met tonight, the patient botanist on his knees as a mud, the physicist who rebuilt an entire instrument from scratch, the scientist willing to publicly doubt his own best discovery, met an unstable, uncertain world by paying closer attention to it, not by looking away. None of them could control what the climate was about to do. What they could control and did again and again across more than half a century was how carefully they were willing to look, and how honestly they were willing to report back what they found even when the answer disappointed them. That more than any single graph feels like the real inheritance worth carrying out of a night like this one. I am deeply grateful you spent these hours with me tonight following one small cold patient thread all the way from a snowy laboratory window in Copenhagen, out to the edge of everything we still do not fully understand. Stories like this one take a great deal of care to put together properly, checking each fact the way Dansgaard checked his own numbers, and having you here listening all the way to the very end, patient enough to sit with uncertainty rather than demanding a tidier ending than the evidence allows means more to me than I can easily put into words. If tonight's journey gave you something worth carrying with you, whether that is a new way of looking at the ground beneath your feet, a little more patience for the parts of your own life that refuse to resolve neatly, or simply a few hours of calm before sleep finally takes over, I would love for you to let me know down in the comments. Tell me which part of tonight's story stayed with you longest. I go through every single one, and I mean that. And if you have not already, consider staying close by for whatever story comes next, because there are a great many more of these quiet buried threads still waiting out there patiently for someone willing to listen closely enough to hear them. Like a share, a moment spent subscribing before you drift off all of it helps this small, careful kind of storytelling find its way to somebody else out there who might need a calm, thoughtful hour just as much as you did tonight. Sleep well tonight, and I will see you again soon for the next story.